Before cereal reaches your bowl, they go through a factory transformation most people never see. If one step in the creation of these products goes wrong, hundreds of thousands of dollars are wasted. Today, we will answer the question of how Cheerios, Frosted Flakes, and Lucky Charms get produced with the most insane precision on Earth. A Cheerios ring begins as pressure trapped inside cooked oat dough. The dough is not shaped like cereal at first. It starts as a dense, warm mass made from whole grain oat flour, water, starches, sugar, salt, and small measured ingredients that help the cereal cook, expand, toast, and hold its shape. The entire process is designed to turn heavy grain into a light ring with a crisp wall and a hollow center. Whole oats arrive at the mill and pass through cleaning equipment. The oats move across vibrating screens that separate dust, broken pieces, and oversized material. Air currents lift away light chaff. Magnets remove tiny metal fragments. The cleaned oats continue into dehulling machines. Each oat kernel has a tough outer hull. The hull must be removed before the grain can become cereal flour. Dehulling equipment cracks and loosens the outer shell while keeping the inner groat usable. The separated hulls are pulled away by air and screening systems. The oat groats then move into milling equipment. Rollers and grinders reduce the groats into whole grain oat flour. The flour is not a fine bakery powder only. It must have the correct particle size for cooking, hydration, and extrusion. Too coarse, and the dough will not form smoothly. Too fine, and the dough may become sticky and difficult to shape. The oat flour is stored in silos or bins before mixing. Pneumatic conveyors move it through enclosed pipes using air pressure. The flour flows like a pale, dry stream into weighing systems. Load cells measure each batch before it enters the mixer. In the mixing area, oat flour meets water. The dry flour darkens slightly as it hydrates. Mixers turn with heavy paddles or rotating arms, folding the ingredients into a damp, thick dough. Sugar, salt, starch, and other dry ingredients are added in controlled amounts. The mixture becomes heavier as the oat particles absorb moisture. This is still only the first stage. The dough must be cooked before it can puff into the familiar ring. The hydrated mixture enters a cooker or preconditioner. Steam and heat soften the oat starches. The dough thickens and becomes more plastic. Inside the machine, rotating screws move the material forward while mixing and compressing it. Heat gelatinizes starch, which means the starch granules absorb water, swell, and form a cooked structure. The cooked dough is dense and smooth. It no longer behaves like flour and water. It behaves like a warm paste with enough strength to hold pressure. This cooked mass is the base that will later expand. The dough then moves toward the extruder. The extruder is a long barrel fitted with one or more rotating screws. The screws grab the cooked dough and push it forward. As the dough travels through the barrel, pressure builds. Friction, steam, and controlled heating keep it hot and workable. The end of the extruder contains the die. This die is the key to the Cheerios shape. It has small openings designed to form the ring. The cooked dough is forced through these openings under pressure. As it exits, the pressure drops suddenly. Moisture inside the hot dough flashes into steam, causing the material to puff. The cereal emerges in tiny ring shapes. The center hole is formed by the die geometry. The dough expands outward, but keeps the circular structure. The fresh pieces are soft, warm, and not fully crisp yet. They look like cereal, but they still contain too much moisture. A cutting mechanism slices the extruded rings to the correct thickness. The cutter moves rapidly across the die face or rotates in front of it. Each cut releases another small ring. The pieces drop onto a conveyor in a steady stream. At this point, the rings are fragile. They must be dried before they can be toasted properly. The cereal enters a drying system, where warm air removes moisture gradually. The rings tumble or travel over perforated belts, while heated air passes through them. Moisture leaves the surface first, then moves from the center of each piece outward. Drying must be controlled carefully. If the outside dries too fast, the ring can crack. If it stays too moist, it will not toast evenly. The goal is a stable cereal piece with enough structure to survive the next high heat stage. After drying, the rings enter the toaster. This is where the pale oat pieces become crisp and lightly browned. Hot air moves around the cereal as the pieces tumble or ride through the oven. The surface dries further, the texture becomes brittle, and toasted oat aromas develop. The ring wall changes during toasting. It becomes lighter, firmer, and more porous. The cereal snaps more cleanly when broken. The color shifts from pale beige to a warmer golden tone. Every piece must reach the correct balance of crispness and moisture. The toasted cereal exits the oven and enters a cooling zone. Air flows across the rings to remove heat. Cooling prevents condensation inside later packaging. It also stabilizes the texture before coating or final handling. Some Cheerios varieties move through a coating drum after toasting. For plain Cheerios, this step may be minimal compared with flavored versions. For sweeter or flavored varieties, syrup, flavor, honey, sugar, cocoa, fruit flavor, or other coating systems can be applied. In a coating drum, cereal rings tumble while a liquid coating sprays onto them. The drum rotates slowly, lifting and folding the cereal so the coating spreads evenly. Nozzles atomize the syrup into fine droplets. The droplets hit the moving rings and cling to the surface. After coating, the cereal may pass through another drying stage. Warm air removes water from the coating and locks it onto the ring. The surface becomes dry enough that pieces do not stick together. The cereal keeps its separate, free-flowing form. The rings then move through screening equipment. Broken pieces and fines fall through mesh openings. Oversized clumps are separated. Airflow may lift away light dust. The goal is an even stream of properly formed rings moving toward packaging. Inspection systems check the cereal before it enters the bagging area. Optical sorters can detect unusual color, dark pieces, or shape defects. Metal detectors check the flow for unwanted fragments. Any rejected material is removed automatically from the product stream. The accepted cereal travels to large holding bins above the packaging machines. These bins act as buffers. They keep the packaging line supplied even as upstream cooking and toasting continue at a steady rate. The cereal flows downward by gravity into weighing systems. Multi-head weighers divide the cereal into small portions. Each weighing bucket holds a measured amount. The control system combines several buckets to reach the exact package weight. Once the correct combination is selected, the gates open and the cereal drops into a forming tube. The inner bag is made from a roll of flexible packaging film. The film unwinds, bends around a forming collar, and becomes a vertical tube. A heat sealer closes the back seam. The weighed cereal drops into the tube. Then horizontal seal jaws close across the top and bottom, creating a sealed bag. The bag must protect the cereal from moisture. Crisp cereal becomes soft if it absorbs water from the air. The film barrier and sealed seams help keep the texture stable. The filled inner bag moves toward the cartoning machine. Flat paperboard blanks feed from a magazine. Each blank is opened into a rectangular box shape. The cereal bag is inserted into the open carton. Mechanical guides keep the bag upright while the carton folds around it. The bottom and top flaps are closed by folding rails. Adhesive or locking tabs secure the carton. The box passes through compression belts that press the flaps into place. The carton becomes square, firm, and ready for coding. A coder prints production information on the box. The mark may include a batch code, plant code, line code, and time reference. The print head applies the code quickly as each box passes. Finished boxes move through check weighers. A box that is too light or too heavy is rejected. Vision systems can check flap closure, print position, and carton orientation. Proper boxes continue into case packing. Frosted flakes begin as hard corn grits entering a pressure cooker. The grits are not flakes yet. They are small broken pieces of corn endosperm, selected for size, hardness, and cooking behavior. Each piece must be strong enough to survive handling, but soft enough to flatten after cooking. The entire factory sequence is built around changing those dense corn particles into thin, toasted flakes, with a dry sugar coating. Before cooking, the corn grits pass through cleaning and sorting equipment. Vibrating screens remove fines and oversized pieces. Air separators lift away light dust. Magnets pull out tiny metal fragments. Optical sorters can remove discolored particles. The goal is a clean, even stream of grits with a narrow size range. The cleaned grits move into weighing hoppers. Load cells measure each batch. Water, sugar, salt, malt flavoring, and other formula ingredients are prepared in separate feed systems. The ingredients must enter the cooker in the correct ratio because the corn needs to absorb moisture and flavor evenly before it can become a flake. The cooker is a sealed vessel built to handle heat and pressure. Corn grits enter through the top or side. Water and flavoring ingredients follow. The vessel closes and steam begins heating the mixture. Inside, the grits absorb moisture. Their hard centers soften. Starch granules swell and begin gelatinizing. The cooker rotates or mixes the batch so every corn particle receives heat and moisture. The movement is slow and heavy. The grits scrape, tumble, and roll inside the vessel while steam pressure builds around them. At the start, each piece is firm and dry. By the end of cooking, each piece has become flexible and slightly sticky. Cooking is one of the most important stages. If the corn is undercooked, it will crack instead of flattening. If it is overcooked, it can smear during flaking. The target is a cooked grit that is soft through the center, but still strong enough to become a distinct flake. After cooking, the hot grits discharge from the cooker. They are now darker, moist, and tender. They do not yet look like cereal. They look like swollen pieces of cooked corn. Steam rises from the mass as it spreads onto conveyors. The cooked grits move into a tempering stage. Tempering allows moisture to equalize inside each piece. The outside of a cooked grit may be wetter than the center. Resting time lets moisture migrate inward and outward until the particle becomes more uniform. This makes flaking smoother. During tempering, the grits sit in bins or move slowly through controlled holding equipment. The temperature and moisture continue balancing. The texture becomes less sticky and more elastic. Each grit becomes ready for flattening. Next comes the flaking mill. Two large steel rolls sit close together with a narrow gap between them. The rolls rotate toward each other. Cooked grits feed into the gap in a controlled layer. Each grit is caught between the rolls and squeezed flat in an instant. The transformation is sharp and mechanical. A thick corn piece becomes a thin flake. The pressure spreads the softened starch outward. The shape becomes irregular, with slightly uneven edges. These irregular edges give frosted flakes their natural-looking flake shape. The roll gap controls thickness. If the gap is too wide, the flakes remain thick and dense. If it is too narrow, they may tear or become too fragile. The mill must flatten the grits enough to create crisp flakes, while keeping them strong enough to travel through the rest of the line. Freshly rolled flakes are pale, moist, and flexible. They bend instead of snapping. They need heat to become crisp. The flakes enter a drying stage before toasting. Warm air removes part of the moisture. The flakes travel over perforated belts or through rotating dryers while air passes through the moving bed. Moisture leaves the flake surface first, then moves from the interior outward. Drying prepares the flakes for the toaster. It reduces stickiness and keeps the flakes separate. It also helps the toaster create a crisp texture rather than a leathery one. The flakes become lighter and less flexible as they dry. The toaster is where the cereal develops its final base texture. Flakes enter a high-temperature oven or rotary toaster. Hot air surrounds them. The flakes lift, tumble, and move through the heating zone. Their surfaces brown slightly. Their moisture drops further. Starch structure sets into a brittle form. The sound inside the toaster is dry and constant. Thousands of flakes move against metal surfaces and against one another. The pieces become lighter, crisper, and more aromatic as the heat passes through them. Toasting must be carefully controlled. A flake that is too pale may taste underdeveloped and soften quickly. A flake that is too dark can taste scorched. The target is a golden toasted cornflake with a dry snap and enough strength for coating. After toasting, the flakes pass through cooling air. Cooling stabilizes the cereal before frosting. If sugar coating hits flakes that are too hot, it can spread too quickly or become uneven. If the flakes are too cool or too dry, coating adhesion can change. The line controls the temperature before the next transformation. The frosting system begins with sugar syrup. Granulated sugar and water are combined in a syrup tank. Heat dissolves the sugar. The liquid turns clear and glossy. The syrup may include flavoring and small formula ingredients that help the coating dry correctly. Agitators keep the syrup uniform, while temperature control keeps it pumpable. The syrup must have the right solids level. If it is too thin, it will soak into the flakes and make them limp. If it is too thick, it may form heavy spots or clumps. The syrup must spray evenly and dry into a thin frosted layer. The toasted flakes enter a rotating coating drum. The drum turns slowly, lifting the flakes and letting them fall in a continuous curtain. Spray nozzles aim heated sugar syrup into the tumbling cereal. The syrup hits the moving flakes as fine droplets. The coating does not cover every flake like paint in one pass. It builds through repeated contact. A droplet lands, spreads slightly, and sticks. Another rotation exposes a new surface. More syrup lands. The flakes roll over one another, distributing the coating across the batch. This is the key difference between plain corn flakes and frosted flakes. The toasted corn base receives a controlled sugar layer that dries into a pale, crystalline finish. The coating adds sweetness, surface texture, and the slightly rough frosted look. The coated flakes leave the drum tacky and warm. They cannot be packed yet. They would stick together and lose crispness. They enter a finishing dryer. Warm air passes through the coated cereal. Water evaporates from the sugar syrup. The coating changes from sticky liquid to dry crystalline film. The flakes separate again as the surface hardens. The cereal becomes free-flowing, crisp, and lightly glossy. The drying step must remove enough moisture to protect crunch. Too much remaining moisture makes the cereal clump. Too much drying can make flakes brittle and powdery. The system balances air temperature, airflow, bed depth, and residence time. After drying, the frosted cereal moves into a cooler. Ambient or conditioned air brings the temperature down. Cooling prevents moisture condensation inside packaging. It also strengthens the sugar coating so it can survive conveyors, hoppers, and weighers. The cooled flakes pass through screening systems. Small broken flakes and sugar dust fall through mesh screens. Oversized clusters are separated. Airflow can remove light fines. The cereal stream becomes more uniform before inspection. Inspection equipment checks the flakes as they move toward packaging. Metal detectors scan the flow. Optical systems can detect dark flakes, pale flakes, clumps, and unusual particles. Reject gates or air jets remove material that does not match the set limits. The accepted cereal flows into surge bins above the packaging machines. These bins keep the packaging line supplied while the cooking, flaking, toasting, and coating systems continue running. The flakes drop from the bins into weighing equipment. Multi-head weighers measure the cereal by combining small portions from several buckets. Each bucket holds a different amount. The control system chooses the best combination to reach the package weight. Gates open, and the measured cereal drops downward. The inner bag forms from a roll of flexible film. The film unwinds and wraps around a forming tube. A vertical heat seal closes the back seam. The measured frosted flakes fall into the open tube. Horizontal sealing jaws close across the film, forming the top of one bag and the bottom of the next. The sealed bag protects the flakes from moisture. This is critical because the cereal's crisp texture depends on staying dry. The sugar coating also needs a barrier from humid air. Lucky Charms production starts with 2 separate product streams moving toward one final blend. One stream becomes toasted oat cereal. The other becomes dry, colourful marshmallow pieces. They are manufactured apart because they behave completely differently. The oat cereal needs heat, pressure, shaping, drying, and toasting. The marshmallow pieces need syrup cooking, aeration, colouring, shaping, and controlled drying. Only after both streams are stable can they be mixed without breaking or sticking. The cereal stream begins with whole grain oats. The oats are cleaned before they are milled. They move across vibrating screens that remove dust, small broken material, and oversized particles. Air separators pull away light chaff. Magnets catch small metal fragments. The cleaned oats continue into dehulling and milling systems. The outer hull of the oat is removed to expose the usable groat. The groats are then milled into oat flour. The flour must have a controlled particle size. It cannot be too coarse, or the dough will form rough, weak pieces. It cannot be too fine, or the mixture can become sticky and difficult to move through cooking and extrusion equipment. The oat flour is stored in bins before mixing. Pneumatic conveyors move it through enclosed lines using air pressure. The flour enters weigh hoppers, where the batch is measured. Small ingredient systems add sugar, salt, starches, and other dry components. Water enters through a metered line. Inside the mixer, the dry oat flour changes into a damp dough. Heavy paddles fold the water into the grain. At first, the mixture looks loose and uneven. As hydration continues, the particles swell and bind together. The dough becomes heavier, warmer, and more uniform. The hydrated dough moves into a cooker or preconditioner. Steam heats the mixture, while rotating screws or paddles keep it moving. The oat starch absorbs water and gelatinizes. This step gives the dough the plastic structure needed for shaping. Without proper cooking, the cereal would crumble instead of expanding cleanly. The cooked dough leaves the preconditioner and enters an extruder. The extruder barrel contains rotating screws that push the dough forward. Pressure rises as the material approaches the die. Heat and pressure work together, turning the dough into a compact, elastic mass. The die at the end of the extruder gives the cereal its shape. Lucky Charms cereal pieces are not simple rings like some oat cereals. They are small shaped pieces, often with curved or clover-like forms. The die openings control the outline. As the hot dough exits the die, pressure drops quickly and moisture inside the dough flashes into steam. The pieces puff slightly as they are cut. A rotating knife slices the extruded dough into small cereal shapes. Each cut releases another piece. The pieces fall onto a conveyor while still warm and soft. They already have their basic shape, but they are not yet crisp. The cereal pieces enter a dryer. Warm air passes around them to remove moisture. The drying must be gradual. If the surface dries too quickly, the pieces can crack. If too much moisture remains, the toaster cannot create a clean, crisp texture. The dryer turns soft oat shapes into firmer pieces that can handle toasting. The cereal then moves into a toaster. Hot air surrounds the pieces as they tumble or travel through the oven. The surface darkens slightly. The texture becomes brittle and light. Toasted oat aroma develops as moisture drops to the final range. The cereal becomes crisp enough to keep its shape in the box and in milk. After toasting, the cereal is cooled. Air flows across the pieces and carries away heat. Cooling prevents condensation in later packaging and keeps the texture dry. The cereal then passes through screens that remove fines, broken pieces, and oversized clusters. While the oat cereal is being formed, the marshmallow stream is built in a different part of the process. The marshmallow pieces begin with a sugar syrup. Sugar, corn syrup, and water enter a heated mixing vessel. The liquid warms and dissolves into a smooth syrup. The syrup must be concentrated enough to dry into a crisp structure, but still fluid enough to pump and whip. Gelatin or another aerating structure is prepared separately. It hydrates in water, then warms into a smooth solution. When added to the syrup, it helps the mixture hold air. The syrup is then moved into a whipping system. Air is worked into the syrup at high speed. The dense liquid expands into foam. Tiny bubbles fill the mixture, giving it a light interior. The foam becomes paler and thicker as air cells form. This is the opposite of the cereal stream, where pressure and heat create expansion. Here, mechanical whipping builds the internal structure. The marshmallow foam is divided into separate color batches. Each batch receives its own color and flavor system. The mixing has to be complete because streaks would show clearly in the finished pieces. The colors must remain strong after drying, so the wet foam is made more intense than the final dried piece may appear. The colored foam is shaped into the familiar tiny marshmallow forms. It may be extruded through shaped dies, deposited into molds, or formed into sheets that are later cut. The shapes are small, with sharp edges and simple outlines so they can dry evenly and survive handling. Fresh marshmallow shapes are soft and sticky. They cannot be blended with cereal yet. They move into a drying system where warm, controlled air removes moisture. The surface firms first, then the interior dries. The pieces become lighter and more brittle as the water leaves. The drying step changes the marshmallow from soft foam into a crisp cereal inclusion. The finished piece is porous, colorful, and dry. It breaks with a light crunch instead of stretching. This texture allows it to remain separate in the cereal box. The marshmallow pieces are screened after drying. Dust, broken fragments, and misshaped pieces fall away. The accepted pieces move into storage bins. Each color and shape can be held separately, then metered later into the final blend. Now the two streams come together. The toasted oat cereal flows from its holding bin. The marshmallow pieces flow from their own bins. Feeders meter each component into a blending drum or blending conveyor. The ratio must be controlled carefully. Too much cereal changes the appearance of the mix. Too many marshmallows can throw off weight distribution and packaging consistency. The blender moves gently. It lifts, turns, and folds the cereal with the marshmallow pieces without crushing them. This is important because the two components have different strengths. Toasted oat cereal is light, but more resistant to handling. Dried marshmallows are crisp and can fracture if the mixing is too aggressive. The blend becomes visually balanced as the colored pieces spread through the oat cereal. The machine does not grind or press the mixture. It simply turns the stream over itself until the distribution is even. After blending, the cereal passes through inspection. Metal detectors scan the product stream. Optical systems can identify dark cereal pieces, pale pieces, broken clusters, or foreign colored particles. Screens remove dust and small broken fragments. Reject gates remove anything outside the limits. The finished Lucky Charms blend then enters surge bins above the packaging machines. The bins hold enough product to keep the packers running smoothly. The blend flows downward by gravity, but but the hopper design must prevent separation. If the heavier cereal and lighter marshmallows separate too much, the final boxes would not contain a consistent mixture. The industrial strawberry layer cake manufacturing sequence begins at the bulk dry storage terminal. Large-scale suction blowers move sifted pastry flour into the primary weight hoppers. These hoppers utilize load cells to ensure a precision of within 100 grams. A secondary pneumatic line introduces powdered glucose into the flour stream. The glucose prevents the starch from retrograding during the freezing process. Sodium bicarbonate is injected at a ratio of 2 kilograms per metric ton of flour. This leavening agent reacts with acidic components to create the crumb structure. A Z horizontal ribbon blender rotates to achieve a 99% homogeneity rating. The hydration phase starts inside a twin-screw continuous mixing unit. Liquid whole eggs are metered into the chamber at a constant flow rate. These eggs are chilled to 5 degrees Celsius to prevent protein denaturation. A high-pressure pump injects vegetable oil through a series of micro nozzles. The oil coats the flour particles to inhibit excessive gluten development. Deionized water is added to reach a specific gravity of 1.05 for the batter. A jacketed cooling system keeps the mixing chamber at a steady 18 degrees Celsius. This temperature control is vital for the stability of the chemical leavening agents. The aeration stage uses a high shear rotostator head to incorporate nitrogen gas. Nitrogen provides a finer bubble structure than standard atmospheric air. The resulting batter density is measured by an inline densitometer. This device sends real-time feedback to the gas flow controller. A batter density of 0.45 grams per cubic centimeter is the target for this recipe. The batter travels through stainless steel piping to the manifold depositor. This manifold spans the width of a 1 meter wide steel conveyor belt. Individual piston pumps discharge 60 milliliters of batter into silicone-coated molds. The molds move into a direct gas-fired tunnel oven with 12 independent heat zones. Zone 1 operates at 140 degrees Celsius to facilitate initial lift. The belt speed is calibrated to ensure a 20-minute residence time. Moisture sensors at the midpoint monitor the humidity levels of the oven atmosphere. High humidity prevents the formation of a thick crust on the sponge surface. Zone 6 reaches a peak temperature of 190 degrees Celsius. This heat triggers the caramelization of surface sugars for color development. The final zones gradually reduce the temperature to set the internal cake matrix. Automatic vacuum depanners lift the baked sponges from the molds at the oven exit. The sponges are placed onto a modular plastic cooling belt. This belt travels through a HEPA-filtered cooling tunnel for 30 minutes. Ambient air is pulled through the sponges to remove internal heat. The core temperature must reach 22 degrees Celsius before the slicing phase. A battery of reciprocating serrated blades cuts the sponges into 3 equal layers. The blade height is adjusted by microservos based on laser thickness measurements. Each layer is diverted to a separate conveyor for specific ingredient application. The strawberry coulis production wing operates as a closed-loop thermal system. Frozen strawberry blocks are pulverized by a high-torque industrial crusher. The resulting slurry moves into a vacuum evaporator to concentrate the natural sugars. Evaporation occurs at 60 degrees Celsius to preserve the volatile flavor compounds. Liquid pectin is injected into the concentrate to establish a thermo-reversible gel. The pH is adjusted to 3.2 using a concentrated lemon juice buffer. This acidity is necessary for the pectin to form a stable molecular network. The coulis is then passed through a fine mesh filter to remove seeds. A plate heat exchanger cools the coulis to 8 degrees Celsius for immediate use. The first applicator station uses a waterfall distributor to coat the base layer. A weight check scale verifies that 40 grams of coulis are applied to each cake. The second sponge layer is placed on top by a high-speed vacuum pick-and-place unit. A second applicator deposits a layer of strawberry-infused cream over the middle sponge. This cream contains stabilized dairy fats and emulsified strawberry solids. The third sponge layer completes the vertical stack before the primary icing phase. The outer frosting is prepared in a pressurized aeration tank for maximum volume. Anhydrous milk fat is blended with sugar syrup and natural stabilizers. The mixture is whipped at 500 revolutions per minute under 3 bars of pressure. This process creates a stable foam with a shelf life of 12 days. The frosting is pumped to a dual-axis robotic icing station. The cake rotates on a pedestal while a side scraper applies the frosting. A top spreader levels the frosting to a thickness of 4 millimeters. Optical cameras inspect the coverage for any gaps or uneven patches. Decorative strawberry rosettes are formed by a multi-nozzle extrusion head. This head uses a star-shaped aperture to create the traditional fluted texture. The extrusion pressure is synchronized with the conveyor belt speed. A secondary station applies a fine mist of pectin glaze over the frosting. This glaze prevents the frosting from drying out during storage. Fresh strawberry quarters are placed into the rosettes by a vision-guided robotic arm. These strawberries are pre-treated with an ascorbic acid wash to prevent browning. A final dusting of pulverized dextrose is applied for visual contrast. The cakes enter a spiral blast freezer for rapid stabilization. Liquid carbon dioxide is sprayed into the chamber to reach -40 degrees Celsius. This rapid cooling creates small ice crystals to preserve the cake texture. The cakes spend 45 minutes inside the spiral freezer. An automated pusher arm moves the frozen cakes toward the packaging line. Cardboard flats are folded into boxes by a mechanical mandrel system. A plastic liner is inserted into each box to prevent moisture loss. The cakes are lowered into the boxes by a soft grip robotic hand. A metal detector scans every boxed cake for potential physical contaminants. This unit can detect ferrous particles as small as 0.5 millimeters. Any rejected boxes are diverted to a secondary inspection bin. A weight grader ensures the final product meets the 500-gram specification. The boxes are sealed with a tamper-evident adhesive strip. An inkjet coder prints the batch number and the production timestamp. The boxes are stacked into corrugated shipping cases by a robotic palletizer. These cases are then wrapped in polyethylene film for structural stability. The palletized goods are moved into the high bay cold storage warehouse. This facility uses an automated storage and retrieval system for inventory management. The temperature is maintained at -18 degrees Celsius with zero fluctuation. Loading docks are equipped with thermal seals to prevent heat ingress during shipping. Every delivery truck is monitored via GPS for real-time temperature tracking. This data is logged into the Quality Assurance Database for compliance. The entire production line can output 800 cakes per hour. This efficiency is achieved through the total integration of mechanical and digital controls. The cleaning in place system cycles through the entire piping network every shift. Hot caustic solution removes fat deposits from the mixing and pumping units. A secondary acid wash neutralizes any mineral scale in the heating elements. The final rinse uses sterilized water to ensure a zero residue environment. All wastewater is treated in an on-site filtration plant before discharge. This plant recovers 90% of the water for non-food industrial use. The factory operates on a 24-hour cycle to maximize equipment utilization. This rigorous process ensures the consistency of the industrial strawberry layer cake. The air quality in the assembly room is monitored for microbial counts. Surface swabs are taken from the conveyor belts every 4 hours. These samples are incubated in the laboratory to check for yeast and mold. The flour silos are equipped with explosion venting panels for safety. Dust collection systems pull fine particles away from the mixing stations. The grease used in the mechanical bearings is food grade certified. All electrical panels are NEMA rated for protection against high pressure washdowns. The facility utilizes LED lighting to reduce heat generation in the cooling zones. The vegetable oil is stored in nitrogen blanketed tanks to prevent oxidation. These tanks are equipped with ultrasonic level sensors for inventory tracking. The sugar syrup is kept in heated vats to prevent crystallization. All raw ingredients are barcoded upon entry for full traceability. This allows the factory to track a single cake back to the specific wheat harvest. The conveyor motors utilize variable frequency drives for precise speed control. These drives reduce energy consumption during periods of lower production. The central control room monitors every motor and sensor in the building. The robotic arms are programmed using a proprietary motion control language. These programs allow for rapid changeovers between different cake sizes. The ultrasonic blades are sharpened using a specialized grinding unit every weekend. This maintenance ensures the cleanest possible cut for the sponge layers. The silicone molds are inspected for surface degradation after every 1,000 cycles. Worn molds are recycled to prevent any silicone migration into the batter. The packaging cardboard is sourced from sustainably managed forests. This commitment to materials ensures the long-term viability of the production model. The industrial fabrication of brownies begins with the high-volume intake of raw commodities. Bulk storage silos hold up to 50 tons of specialized pastry flour. This flour features a low protein content to ensure a tender crumb. Pneumatic transport lines move the flour into the primary sifting station. Vibratory screens remove any particles larger than 200 microns. Cocoa powder arrives in hermetically sealed containers to prevent moisture absorption. This cocoa is typically alkalized to reach a pH level of 7. The alkalization process darkens the powder and mellows the flavor profile. Automatic scales measure the cocoa with an accuracy of 10 grams. A separate line delivers granulated sucrose from a central hopper. The sugar is pulverized into a fine mesh to facilitate rapid melting. Liquid fats are stored in stainless steel vats with internal heating coils. These coils maintain the fat at a constant 45 degrees Celsius. This temperature prevents the lipid chains from crystallizing in the pipes. Refined soybean oil provides the necessary moisture for a fudgy texture. Some formulations utilize anhydrous milk fat for a richer mouthfeel. The primary mixing phase utilizes a high-torque industrial blender. The liquid fats enter the mixing chamber through pressurized nozzles. Cocoa powder is added next to create a thick chocolate paste. This stage is known as the wet rub in the baking industry. The friction from the blades raises the paste temperature slightly. Infrared sensors monitor this heat to prevent scorching of the cocoa. A secondary mixer prepares the hydration base for the batter. Liquid eggs are pumped from refrigerated tanks at 4 degrees Celsius. These eggs undergo inline pasteurization before they reach the blender. A plate heat exchanger flashes the eggs to 60 degrees Celsius. They are immediately cooled back to 10 degrees Celsius. This process eliminates pathogens without coagulating the egg proteins. Natural humectants, like vegetable glycerin, are added to the egg mix. Glycerin binds water molecules to the starch during the baking cycle. This chemical bond prevents the brownie from becoming stale. The dry ingredients meet the wet base in a continuous mixer. The flour is folded in by a twin screw agitation system. This system prevents the overdevelopment of gluten in the wheat. Excessive gluten would make the brownie tough and bread-like. Salt is injected into the stream at a precise 0.2% ratio. It acts as a flavor enhancer for the chocolate components. A small amount of sodium bicarbonate provides a chemical lift. This leavening agent reacts with the acidic cocoa particles. The batter moves through a series of refining rollers. These rollers reduce the particle size of the sugar and cocoa. A final particle size of 30 microns ensures a smooth mouthfeel. The refined batter is pumped into a vacuum de-aeration tank. This tank removes any trapped air bubbles from the mixing stage. Removing air increases the density of the final brownie slab. A dense structure is required for the fudge classification of the product. The batter reaches a final viscosity of 15,000 centipoise. Industrial brownies often feature inclusions like semi-sweet chocolate chips. These chips are stored in a climate-controlled room at 18 degrees Celsius. This prevents the chips from blooming or sticking together. A vibratory feeder dispenses the chips into the moving batter line. A static mixer folds the inclusions in without shearing them. The ratio of inclusions is usually 10% of total weight. The batter is now ready for the depositing stage. A high-speed manifold spans the width of the production conveyor. This manifold contains 24 individual piston-driven nozzles. The nozzles deposit the batter into large steel baking trays. These trays are coated with a permanent Teflon layer. An automated sprayer applies a secondary film of vegetable oil. The oil ensures a clean release after the cooling phase. Each tray receives exactly 12 kilograms of brownie batter. Optical sensors verify the weight and level of every tray. A mechanical oscillating plate spreads the batter to the corners. This ensures the brownie slab has a uniform thickness of 30 millimeters. The trays enter a multi-zone convection tunnel oven. The oven is 60 meters long to accommodate high-speed production. It is heated by a series of natural gas burners. The first zone is set to 150 degrees Celsius. This initial heat initiates the melting of the sugars. The second zone increases the temperature to 170 degrees Celsius. This is the primary baking phase where the structure sets. Convection fans circulate the air at 5 meters per second. This constant airflow ensures the edges do not burn before the center. Steam injection ports maintain a 40% humidity level. The humidity prevents the top surface from cracking or crusting. The final oven zone facilitates the Maillard reaction. This chemical reaction occurs between the sugars and amino acids. It creates the complex flavor profile associated with baked chocolate. The total residence time in the oven is 28 minutes. An automated arm extracts the hot trays at the oven exit. The trays move onto a modular plastic cooling belt. This belt travels through a spiral cooling tower. Filtered air at 15 degrees Celsius blows across the trays. The cooling process must be gradual to prevent the slab from shrinking. The internal temperature must drop to 25 degrees Celsius. This cooling phase typically lasts for 45 minutes. A vacuum depanner lifts the entire brownie slab from the tray. The slab is placed onto a high-density polyethylene cutting board. This board moves toward the ultrasonic slicing station. Ultrasonic blades vibrate at 20,000 Hz per second. This vibration prevents the dense brownie from sticking to the knife. The blades make vertical and horizontal cuts simultaneously. This creates perfectly square units with sharp edges. The standard size is 5 centimeters by 5 centimeters. Any trim from the edges is diverted to a rework bin. This trim is ground up for use in other chocolate products. The individual brownie units are separated by a divergent conveyor. This conveyor increases the space between the brownies for packaging. Some brownies pass through an enrobing station for a chocolate coating. The enrober pours a curtain of tempered chocolate over the units. A blower clears the excess chocolate to maintain a thin layer. The coated brownies enter a secondary cooling tunnel. This tunnel sets the chocolate coating to a high gloss finish. the brownies move into the primary packaging zone. A robotic arm picks up 4 brownies at a time. It places them into a pre-formed plastic blister tray. The tray provides structural support during shipping and handling. A flow wrap machine encapsulates the tray in a polymer film. This film is treated with a nitrogen flush. Nitrogen replaces the oxygen to prevent the oxidation of fats. This gas flushing technique doubles the product's shelf life. The film is heat sealed at both ends by a rotating jaw. A laser printer applies the lot number and expiration date. The individual packs move toward the secondary packaging station. A case packer assembles 24 packs into a corrugated box. This box is sealed with a pressure-sensitive adhesive tape. A check weigher verifies that the case meets the target weight. Any underweight cases are automatically pushed off the line. A palletizing robot stacks the cases onto a wooden pallet. The robot follows a specific pattern to ensure stack stability. A stretch wrap machine secures the load with several layers of plastic. The pallet is tagged with a radio frequency identification label. This label contains the entire production history of that batch. The pallets are moved to a temperature-controlled warehouse. This warehouse is kept at 18 degrees Celsius. Quality control technicians perform a moisture analysis on every batch. They use a halogen moisture analyzer to check for consistency. The target moisture content for a fudge brownie is 12%. A texture analyzer measures the force required to compress the brownie. This ensures the chewiness meets the brand specifications. The cocoa solids are verified using a spectrophotometer. This device measures the light absorbance of the chocolate. The production line operates on a 24-hour schedule. A clean-in-place system sanitizes the mixes between batches. This system uses hot water and biodegradable and detergents. All water used in the plant undergoes reverse osmosis filtration. The factory utilizes a closed-loop energy recovery system. Heat from the ovens is captured to preheat the incoming air. This reduces the carbon footprint of the manufacturing facility. The flour silos are equipped with explosion suppression systems. Fine flour dust can be highly combustible in large volumes. Spark detectors monitor the pneumatic lines for any heat buildup. The packaging room is kept at a positive air pressure. This prevents any dust or insects from entering the clean zone. Workers wear specialized lint-free suits and head coverings. All tools are made from detectable stainless steel. The vegetable oil tanks are nitrogen blanketed to prevent rancidity. Oxygen is the primary enemy of long-term fat stability. The supply chain is tracked using a digital ledger system. Every ingredient can be traced back to its original farm. This level of transparency is standard for industrial food. Production. The brownie recipe is stored in a secure digital vault. The central computer controls every motor and valve in the plant. The automated manufacturing of cheesecake begins with the large-scale processing of the base crust material. Bulk quantities of graham flour and wheat flour are combined in a high-speed industrial shredder. This unit pulverizes the baked biscuits into a uniform crumb with a diameter of 2 millimeters. The crumbs are moved via a vibratory conveyor to a horizontal blending drum. Molten butter is injected into the drum through a series of atomizing nozzles. The butter acts as a binding agent to ensure the crust remains structurally sound. Granulated sugar is added to the mixture to facilitate caramelization during the baking stage. The crust mixture is transferred to the primary molding line by a vacuum lift system. Circular spring-form pans move along a specialized belt at a rate of 40 units per minute. A volumetric depositor drops exactly 100 grams of the crumb mixture into each pan. A pneumatic tamping head descends to compress the crumbs with 50 pounds of pressure. This compression creates a dense and level foundation for the cheese filling. The sides of the pans are simultaneously brushed with a light film of release agent. This prevents the cake from adhering to the metal during the cooling phase. The preparation of the cheese filling occurs in a separate, climate-controlled mixing terminal. Industrial-sized blocks of cream cheese are loaded into a vertical, high-shear mixer. These blocks are tempered to exactly 20 degrees Celsius to ensure maximum pliability. A heavy-duty agitation arm breaks the cheese down into a smooth and aerated paste. Liquid sour cream is introduced through a flow-controlled piping network. The sour cream provides the necessary acidity to balance the richness of the fats. Large quantities of liquid whole eggs are then metered into the mixing chamber. These eggs act as the primary emulsifier and structural setting agent for the batter. Pure vanilla extract is injected into the stream via a microdosing pump. The mixing speed is reduced to avoid the over-incorporation of atmospheric air. Excess air in the batter causes the cheesecake to crack during the thermal expansion phase. The batter is monitored by an inline viscometer to ensure it reaches 4,000 centipoise. A final stage of the mixing process involves the addition of cornstarch. The starch binds to the free moisture to prevent the occurrence of syneresis. The finished batter is pumped through insulated stainless steel lines to the depositing station. A multi-piston manifold accurately dispenses the batter over the prepared crust. Each pan is filled to 90% of its total volume to allow for expansion. The pans are then transferred into a continuous water bath tunnel oven. This oven utilizes a shallow pool of circulating water to regulate the heat transfer. The water bath ensures the temperature never exceeds 100 degrees Celsius at the base. This thermal regulation prevents the edges of the cake from cooking faster than the center. The oven is divided into 4 distinct thermal zones for precise moisture control. Zone 1 maintains a high humidity level of 80% to prevent surface drying. The temperature in this initial stage is set to 120 degrees Celsius. Zone 2 increases the heat to 140 degrees Celsius to set the egg proteins. The moisture levels are gradually reduced in Zone 3 to facilitate color development. A light golden hue is achieved on the surface through controlled convection airflows. The final zone utilizes a cooling gradient to stabilize the cake before it exits the oven. The total residence time within the tunnel oven is approximately 90 minutes. An automated arm removes the pans from the water bath at the end of the line. The cakes enter a primary cooling chamber to reduce the internal temperature to 40 degrees Celsius. This slow cooling prevents the cheesecake from pulling away from the sides of the pan too quickly. The pans move into a blast chiller where the temperature is dropped to 4 degrees Celsius. This rapid cooling stage is essential for the final set of the dairy fats. The cheesecake must reach a firm consistency before the depanning process begins. A mechanical depanner uses a series of gentle suction cups to lift the cake from the mold. The springform rings are automatically expanded and retracted for sterilization. The cakes are placed onto a sanitized plastic transport disc for the finishing stage. Many industrial cheesecakes receive a fruit-based topping at this point in the sequence. A secondary manifold applies a layer of fruit puree or glaze to the top surface. The glaze is heated to 60 degrees Celsius to ensure a smooth and glass-like finish. It is immediately cooled by a localized cold air jet to lock the topping in place. If the recipe requires a swirl pattern, a robotic needle system is utilized. The needles inject colored fruit syrups into the wet batter before the baking stage. The robotic arm follows a pre-programmed geometric path to ensure visual consistency. For decorative borders, a multi-nozzle whipping station applies cream cheese frosting. The frosting is extruded through fluted tips to create a traditional rosette pattern. The cakes then move to the high-frequency ultrasonic slicing station. The ultrasonic blades vibrate at 30,000 Hz to prevent the cheese from sticking. This technology allows for perfectly clean cuts through the dense and sticky filling. The machine can slice the cheesecake into 12 or 16 equal wedges. Each wedge is separated by a thin piece of parchment paper to prevent re-adhesion. The parchment paper is fed from a continuous roll and cut by the same blade. The sliced cakes are moved to the primary packaging terminal by a synchronized conveyor. The packaging process involves placing the cake into a rigid plastic dome. This dome protects the decorative frosting and the delicate top glaze. A cardboard base provides structural support and contains the product information. The packages are moved into a vacuum sealing machine to remove excess oxygen. An inert gas flush is sometimes used to maintain the freshness of the dairy components. The sealed units are then placed into individual retail boxes by a pick-and-place robot. These boxes are constructed from high-grade recycled paperboard with a moisture barrier. A laser printer applies the batch code and the specific expiration date to each box. The boxes are grouped into master cases for bulk distribution to wholesalers. Each master case is tracked by a unique radio frequency identification tag. The cases are stacked on pallets by a heavy-duty robotic palletizing arm. The pallets are wrapped in multiple layers of clear stretch film for stability. The finished product is stored in a deep freeze warehouse at -20 degrees Celsius. This freezing stage allows for long-distance transport without compromising the texture. The quality control department monitors the fat content of every batch using a centrifuge. The moisture to solids ratio is checked using a rapid thermal analyzer. Any batch that falls outside of the 5% variance range is rejected. The pH level of the batter is measured to ensure the sour cream has reacted correctly. A texture analyzer probes the center of a sample cake to measure the resistance. This ensures the mouthfeel is consistent across every single production run. The color of the top glaze is verified using a digital spectrophotometer. The industrial facility uses a centralized control system to manage the ingredient flow. Silos are equipped with ultrasonic level sensors to trigger automatic reordering. The water used in the process undergoes a 3-stage purification sequence. This includes carbon filtration and ultraviolet sterilization to ensure purity. The air in the assembly room is filtered through a series of HEPA units. These filters remove nearly all airborne contaminants from the production environment. The floors are sloped to integrated drainage systems for easy cleaning. Every 4 hours, the entire line undergoes a localized sanitation cycle. High-pressure steam is used to clean the depositor nozzles and mixing blades. The conveyor belts are constructed from antimicrobial blue polyurethane material. This material resists the growth of bacteria and is easy to inspect visually. The factory operates on a 24-hour schedule with 3 shifts of workers. The output can reach several thousand units per hour depending on the cake size. This massive scale is necessary to meet the global demand for frozen desserts. The supply of cream cheese is delivered via refrigerated tanker trucks. These tankers are emptied into the holding vats using a pressurized air system. The butter is stored in a separate heated room to maintain a liquid state. All dry ingredients are passed through a metal detector before entering the mixer. This ensures that no foreign objects from the harvesting process remain in the flour. The packaging materials are stored in a dry zone to prevent mold growth. The logistics team coordinates the departure of refrigerated trucks every 6 hours. Industrial ice cream production begins with the preparation of the liquid mix base. Raw ingredients used in the base include milk or milk solids, cream or anhydrous milk fat, sweeteners such as sucrose or glucose syrup, stabilizers, emulsifiers, and optional flavoring agents. Bulk liquid dairy components are stored in temperature-controlled stainless steel tanks connected to automated dosing lines. Milk fat content is measured using inline infrared sensors to meet formulation targets, typically between 8 and 12% depending on the product specification. Sweeteners such as granulated sugar or glucose syrup are stored in dry bins or heated tanks. Sugar is conveyed using auger screw feeders into blending tanks, while glucose syrup is pumped through jacketed pipelines at a regulated temperature between 45 and 60 degrees Celsius to maintain viscosity. Stabilizers and emulsifiers such as guar gum, mono and diglycerides, or carrageenan are added in precise quantities, using dry ingredient feeders with load cell controlled hoppers. All components are blended in high capacity, jacketed stainless steel mix tanks equipped with high shear agitation. Mixing durations and shear rates are pre-programmed and adjusted based on batch size and viscosity targets. The mixture is heated uniformly to 70-85 degrees Celsius using indirect steam in the jacket to fully dissolve solids and activate emulsification agents. This thermal processing step homogenizes the mixture and ensures complete dispersion of the fat phase. The hot mix is then passed through a homogenizer at pressures ranging from 1500 to 2500 psi. This high-pressure two-stage process reduces the size of fat globules, creating a stable emulsion and improving mouthfeel and overrun stability. Homogenization is measured and recorded by inline pressure transducers and flow meters. Once homogenized, the mix is immediately cooled to below 5 degrees Celsius using plate heat exchangers. The cooled mix is transferred to aging tanks and held between 2 and 5 degrees Celsius for a period of 4 to 24 hours, depending on product type. During aging, the fat crystallizes and proteins hydrate, which enhances body, texture, and whipping properties. Aging tanks are equipped with low-speed agitators to maintain uniformity without incorporating air. After aging, the mix is pumped into continuous freezers. These machines are equipped with scraper blades and barrel chillers. The mix enters at 2 to 5 degrees Celsius and is rapidly frozen as it moves through. The freezing cylinder cooled to approximately 20 to 25 degrees Celsius using ammonia or freon-based refrigeration systems. The freezing barrel incorporates air into the mix during agitation. The amount of air added is called overrun, typically maintained between 60 and 100% by volume using controlled air injection valves synchronized with pump speed. The partially frozen ice cream exiting the continuous freezer has a temperature of 5 to 7 degrees Celsius and a semi-solid texture. From this point, the product flow diverges based on packaging format. For bulk containers, the ice cream is extruded directly into tubs or pails using piston or rotary fillers. For single-serve novelties or molded formats, the product enters downstream portioning or molding stations. In extrusion-based forming systems, the semi-solid ice cream is extruded through stainless steel nozzles onto a moving stainless steel belt cooled to 40 degrees using cryogenic cooling elements. The belt carries the formed shapes under a quick freeze chamber where additional cold air is blown to firm up the shape. Inline sensors monitor form consistency and weight. Shapes are cut by ultrasonic or wire blades synchronized with belt movement. In molded systems, the ice cream is deposited into polycarbonate molds that travel on a carousel immersed in a brine solution held at 25 to 30 degrees. Product solidifies inside the mold within 8 to 12 minutes, depending on volume. Once hardened, sticks are inserted mechanically into the semi-solid mass using servo-driven arms. Demolding is achieved by briefly dipping molds into warm water baths and using pneumatic pistons to eject the bars. Fillings, inclusions, and variegates are added at multiple points. For layered products, rotary depositors add jams, caramel, or chocolate syrup between ice cream layers. Inclusion feeders dose chocolate chips, cookie pieces, or nut fragments into the flowing stream before extrusion using volumetric or gravimetric feeders. Variegates are added, using swirl nozzles or rotating spouts that inject sauces in spiral patterns into tubs. Enrobing stations apply chocolate coatings to frozen bars using curtain coaters or immersion tanks. Bars are transported on wire belts and pass through a curtain of liquid chocolate held at 30 to 35 degrees Celsius. Excess coating is blown off using air knives. Coated bars pass through a set zone where the chocolate is tempered and solidified using directed cold air streams. Toppings such as nut granules or cookie crumbs are applied to the wet coating via vibratory sprinklers before hardening. Once the shape is stabilized and the product fully frozen, packaging begins. Products are loaded into flow wrapping machines or form-fill seal machines. Printed film is drawn from reels, formed around the product, and sealed using heated jaws and pressure. Modified atmosphere flushing may be applied to reduce oxygen exposure. Each package is marked with batch codes and expiry dates via inkjet or laser printers. Packaged products proceed to check weighers and metal detectors for final inspection. Weighing systems use dynamic load cells to ensure each item is within +get 1% of target weight. Metal detectors with triple coil arrays scan for ferrous, non-ferrous, and stainless steel contamination. Rejected products are removed automatically from the line and logged in the manufacturing execution system. After inspection, individual packages are sorted into multi-packs or cartons using robotic collators and carton erectors. Units are loaded into retail-ready boxes, sealed with glue or tape, and labeled with barcode identifiers. Cartons are stacked by robotic palletizers into programmed patterns based on load configuration and distribution route. Stretch wrapping machines secure pallets with film before warehouse transfer. In frozen storage, pallets are maintained at 25 degrees RC or colder. Pallet locations are mapped using barcode scanners integrated into warehouse management software. Products remain in frozen inventory for no more than the shelf life period assigned to each SKU. Rotation is enforced using first expiry, first out logic based on lot and production timestamp. The entire process is supported by centralized SCADA systems that monitor temperature, viscosity, pressure, weight, flow rate, air injection volume, and cooling intensity at every stage. Each unit of ice cream is fully traceable to its ingredient lots and production conditions through digitized batch records stored in the ERP system. The production of frozen yogurt in a factory begins with the preparation of the liquid mix base, which consists of dairy solids, sweeteners, live yogurt cultures, stabilizers, emulsifiers, and water. Each component is handled in isolated supply systems to ensure batch-to-batch consistency before integration. The mix formulation is calculated to achieve a target fat content of 2 to 4%, milk solids non-fat of 8 to 12%, and a final total solids content between 30 and 38%, depending on the product type. Bulk dairy ingredients, such as skimmed milk, whole milk, and cream, are stored in stainless steel, temperature-controlled silos or tanks held between 1 and 4 Allency. These tanks are fitted with slow-speed agitators to prevent fat separation and sedimentation. From the tanks, ingredients are drawn through dedicated pipelines with volumetric flow meters that measure and regulate dosing rates with tolerances within +0.2%. Sweeteners such as sucrose, glucose syrup, fructose, or high fructose corn syrup are stored in either crystalline form or heated tanks depending on their physical state. Crystalline sugars are conveyed to mixing tanks via screw feeders or pneumatic conveyors, while liquid syrups are pumped through heated, jacketed pipes to maintain constant viscosity. The addition rates of each sweetener are determined by pre-programmed recipes in the batching software and are adjusted in real time based on inline refractometers measuring total soluble solids. Stabilizers and emulsifiers such as guar gum, carrageenan, mono and diglycerides, or cellulose derivatives are pre-blended into dry mixes and introduced using vacuum powder hoppers into blending tanks containing preheated water at 60 or 70 degrees Celsius. This temperature is critical for full hydration and dissolution. Agitation is applied using high shear impeller mixers, ensuring uniform dispersion and hydration within 15 to 20 minutes. Viscosity is monitored continuously via inline rotational viscometers, and any deviation triggers automatic adjustment to the water feed rate or agitation speed. Once all ingredients are combined, the resulting mix is pasteurized using a continuous high-temperature, short-time HTST pasteurizer. The pasteurization process typically operates at 85 Celsius for 30 seconds to ensure microbial reduction without altering flavor or functional properties. The system includes balance tanks, timing pumps, regeneration sections, holding tubes, and cooling exchangers. Temperature probes and flow controllers verify that critical control parameters are met for every liter of mix. Any batch failing to meet time temperature integration is automatically diverted to a reject tank. Following pasteurization, the mix is homogenized in a two-stage homogenizer at pressures between 1500 and 2500 psi. The first stage breaks down fat globules to sub-micron sizes, promoting a stable emulsion, while the second stage disperses protein aggregates evenly throughout the mix. Homogenization ensures a smooth mouthfeel, prevents cream separation, and enhances the stability of the yogurt base during frozen storage. The homogenized mix is rapidly cooled to 4 degrees Celsius using a plate heat exchanger and transferred into agitated aging tanks. These stainless steel tanks have capacities ranging from 2,000 to 20,000 liters and are equipped with low-speed paddles to maintain uniform suspension without introducing air. The mix is aged for 4 to 24 hours depending on the formulation. During this aging period, fat crystallization and protein hydration take place, improving the whipping properties and final texture of the frozen yogurt. After aging, the next stage is inoculation with live yogurt cultures, a pre-prepared, freeze-dried culture blend containing specific strains of Lactobacillus, Bulgaricus, and Streptococcus thermophilus is rehydrated and activated in a sterile environment, then introduced into the aged mix in precise ratios. The inoculated mix is transferred to fermentation tanks equipped with temperature control systems. The mixture is held at 43 degrees Celsius for 4 to 6 hours, during which lactic acid is produced, reducing pH from above 6.5 to around 4.5. The acidification process causes protein coagulation, giving the base its distinctive yogurt flavor and slightly thickened texture. Once fermentation reaches the target pH, it is immediately halted by cooling the mix to below 8 degrees Celsius. This temperature shock preserves the live cultures and stabilizes the flavor. From here, the yogurt base may be held in intermediate storage for up to 24 hours before being processed further. If flavorings or colorants are required, they are added post-fermentation to preserve the viability of the live cultures. These additives are introduced through inline dosing pumps, controlled by magnetic flow meters for precise delivery. The chilled fermented yogurt mix is transferred to the continuous freezing units. These industrial freezers use scraped surface barrel designs, where the yogurt base is frozen while being continuously agitated by rotating blades. The barrel wall is chilled to between 20 and 30 degrees Celsius using ammonia or freon-based refrigeration systems. The rotating blades prevent ice crystal growth by constantly scraping the frozen layer from the barrel wall and remixing it into the semi-frozen matrix. During freezing, air is incorporated into the mix to achieve a desired overrun of 30% to 60% by volume, much lower than regular ice. Cream to maintain the dense, creamy consistency associated with frozen yogurt. The air injection rate is precisely controlled using mass flow controllers and synchronized with product flow rate. The resulting product exits the freezer at a temperature of 5 to 7 degrees Celsius and has a soft serve consistency. If inclusions such as fruit pieces, chocolate chips, or granola clusters are required, they are introduced at this stage using rotary feeders or auger-based inclusion systems. These systems are calibrated to dispense particulate matter based on mass or volume per unit of frozen yogurt. Inclusions are mixed gently into the flow using low shear blending heads to avoid damaging texture or shape. Forming and portioning depend on the packaging format. For cups and tubs, rotary or piston fillers dispense the frozen yogurt into containers on an index conveyor line. Fill levels are verified using laser height sensors or load cells beneath the filling stations. The containers are then lidded using pick-and-place robots, followed by heat sealing or snap lid application depending on the package design. For stick products or novelty bars, the yogurt is extruded into polycarbonate molds mounted on a carousel or linear track. The molds pass through a 30°C brine bath or air blast freezer for rapid hardening. Once the product reaches a core temperature of 18 degrees, sticks are inserted using servo-controlled plungers. The molded products are then released from the molds using brief exposure to warm water spray or ultrasonic demolding mechanisms. Products requiring enrobing are transferred to chocolate coating stations. Bars move on a mesh belt through a curtain of tempered chocolate or compound coating held at 32 to 34 degrees Celsius. Excess coating is removed using air knives, and toppings such as crushed nuts or cookie bits are sprinkled over the wet coating before it hardens in a subsequent cooling tunnel maintained at 15 degrees Celsius. Every unit, whether in cup, tub, or stick format, is passed through flow wrappers or form-fill seal machines. Packaging film is drawn over a forming collar, heat sealed along longitudinal and transverse axes, and printed with lot numbers and expiration dates using thermal inkjet systems. Products are checked on inline check weighers for mass accuracy, then metal detected using balanced coil systems capable of detecting contaminants down to 1.0 mmHg ferrous equivalents. Packaged frozen yogurt units are grouped into multi-packs or retail cartons using robotic pick-and-place systems. Cartons are sealed with hot melt glue and printed with barcodes and logistics identifiers. Palletizing robots stack cartons in programmed configurations. Each pallet is wrapped using rotary stretch wrapping machines and moved into blast freezers or deep storage warehouses. Frozen storage areas maintain air temperatures between 25 and 30 degrees Celsius, with controlled airflow to preserve texture and prevent ice recrystallization. Each pallet is tagged with barcodes that link to a warehouse management system, allowing full traceability of production date, ingredient lots, shift information, and packaging batch. The factory production of sorbet begins with the precise formulation of a base mix that typically consists of filtered water, fruit puree or juice concentrates, a combination of sugars, stabilizers, and acidulants. These ingredients are sourced in bulk and stored in isolated silos, refrigerated tanks, or powder silos based on their form and storage requirements. Before batching begins, each raw material is passed through automated intake stations where flow rate, weight, or volume is measured using mass flow meters or load cells to ensure formulation precision to the second decimal. The main batch tank is a large stainless steel jacketed vessel fitted with dual mode agitation, one high shear impeller and one slow speed anchor scraper to manage the simultaneous dispersion of powders and gentle circulation of the mix. The process begins by pumping deionized water into the tank. This water is processed through reverse osmosis filters to reduce mineral content and stabilize the flavor profile. Temperature of incoming water is held at 60 to 70 degrees Celsius to accelerate sugar dissolution and aid in the hydration of stabilizers later in the cycle. Fruit inputs, often high-viscosity purees or concentrates, are pumped from cold storage tanks maintained at gangs. These tanks are fitted with bottom-mounted paddle stirrers to prevent sedimentation of pulp or particulate matter. The fruit component is introduced via jacketed stainless lines with rotary lobe pumps that preserve particulate integrity and ensure steady laminar flow. Inline flow meters measure delivery in real time, adjusting valves based on programmable batch set points. Sweeteners are introduced in multiple phases depending on their type. Crystalline sugars, such as sucrose or dextrose, are stored in bulk bag unloaders and conveyed to the tank using vacuum-driven feeders or screw. Augers, passing through sieve screens to remove agglomerates. Liquid sweeteners, like glucose syrup or high fructose corn syrup, are pumped from preheated tanks through jacketed lines at temperatures between 40 and 60 degrees Celsius to reduce viscosity. All sugar additions are monitored using an inline refractometer, which continuously reads the brix level and automatically adjusts feed rates to ensure consistency in total soluble solids. Stabilizers and emulsifiers, including locust bean gum, guar gum, or pectin blends, are pre-dispersed into a slurry using a high-shear induction system connected to a secondary mixing tank. The system uses a venturi-driven powder funnel that draws dry powders into a vortex of hot water, while shear blades break down clumps. The hydrated stabilizer solution is then metered into the primary batch tank over several minutes to allow for uniform dispersion. Viscosity is tracked by an inline rotational viscometer, while flow rate is synchronized with the agitator speed to prevent localized gelation. Acidulants are introduced once the temperature drops below 60 degrees Celsius to preserve their functional integrity. Citric acid and malic acid are most commonly used, added via microdosing pumps based on real-time pH feedback from inline probes. The typical pH target range for sorbet mix is between 3.4 and 4.2, depending on fruit type and desired tartness. Some blends may also include buffering salts or fruit-derived aromatic extracts, introduced in sub-gram quantities with gear-driven precision pumps. Once the mix is fully blended, the entire volume is passed through a plate or tubular heat exchanger for pasteurization. The product is heated to between 82 and 90 degrees Celsius for a holding period of 20 to 30 seconds using a hot water loop on the heating side of the exchanger. Flow rates are calibrated to ensure that each liter achieves the required thermal profile. Temperature probes at the inlet, outlet, and holding tube ensure compliance with the time temperature curve. Any deviation from set points automatically diverts the mix to a rework tank using pneumatically controlled valves. Following pasteurization, the mix is rapidly cooled to 4 degrees Celsius using chilled glycol in the final section of the exchanger. It is then pumped to aging tanks, insulated, vertical stainless steel silos with gentle agitators. The mix is held for 4 to 24 hours, depending on stabilizer type, allowing the hydration of hydrocolloids and maturation of flavor. During aging, key metrics including brix, viscosity, pH, and color are measured at regular intervals using inline and lab-based sampling. After aging, the mix is transferred to continuous freezers for dynamic freezing. These are horizontal barrel-type scraped surface heat exchangers with internal rotors spinning at high speed. The internal barrel is cooled by ammonia or freon-based refrigerant, keeping the wall temperature at 25 degrees Celsius to 30 degrees Celsius. The mix is pumped into the barrel at 4 degrees Celsius and partially frozen in under 30 seconds. Rotor blades scrape frozen mix from the walls, maintaining even temperature distribution and preventing ice crystal buildup. At this stage, air is injected into the freezing chamber to achieve controlled overrun. For sorbet, overrun levels are typically between 10 and 30%. maintained using mass flow controlled air injection, synchronized with product throughput. Air pressure, temperature, and flow rate are logged continuously. The exit temperature of the product from the freezer is typically 5 degrees C to 7 degrees C, with a soft serve consistency suitable for depositing. At the point of extrusion, some product formats receive inclusions or variegates. For inclusion, dry or semi-moist elements like fruit pieces, citrus peel, or coconut shreds are fed through a belt-based dosing unit with weigh cell feedback. The feeder aligns with the product stream and deposits inclusions just before it enters the filler. Variegates, such as raspberry swirls or mango sauce, are injected via multi-nozzle swirl heads using positive displacement pumps, synchronized with container indexing to create layered or spiral visual effects. The filling system uses rotary or linear piston fillers with programmable dose volumes. Fill heads descend into the container, release the product in a bottom-up motion to prevent air entrapment, and retract at the end of the fill cycle. Laser height sensors verify the final fill level to ensure consistency. For products with decorative topping, a secondary depositor adds surface sources, fragments, or textured swirls before lidding. Filled containers are sealed with pre-cut lids or heat-sealed films. Lidding stations use servo-driven arms and apply uniform pressure to ensure adherence. Date coding and batch marking are applied using thermal inkjet or CO2 laser systems immediately after sealing. Each pack is passed through a metal detector, which uses multi-frequency coils to detect foreign metallic objects within the sealed product. Immediately post-packaging, the product enters the hardening tunnel. This is a spiral or straight belt blast freezer, where ambient air temperature is held at 35 to 45 degrees Celsius. Air is circulated at high speed to ensure fast freezing rates. Dwell time inside the tunnel ranges from 30 to 90 minutes, and the goal is to reduce the core temperature of each unit to below just 18 degrees Celsius. Faster hardening reduces ice crystal size and improves long-term texture stability. Core temperatures are verified by infrared sensors or penetrating thermocouples on randomly sampled units. Hardened products are conveyed to automated carton packers. A vision system identifies each container's orientation and positioning. Robotic arms equipped with suction grippers or mechanical clamps group units into clusters and load them into pre-erected cartons. Cartons are sealed using hot melt adhesive or tape, then labeled using a print and apply labeling system. The label includes SKU identifiers, lot number, date, and logistics barcodes. Cartons are then routed to the palletizer. Layers of cartons are stacked according to a programmed pattern to optimize pallet stability and maximize transport efficiency. Stretch wrapping machines encase each pallet in multi-layered film with preset tension profiles to secure the load during transport. Pallets are labeled with SSCC codes and sent to deep freeze storage, where ambient temperature is maintained between 25 and 30 degrees C. Storage location is recorded in a warehouse management system using RFID or barcode scanning. Each batch of sorbet is traceable through electronic production records, linking ingredient lots, formulation parameters, processing times, and packaging data. Digital records include metrics for pasteurization, Brix values, overrun, pH, freezing rate, fill weight, inclusion density, and packaging inspection results. Production lines are modular and allow for multiple flavor variants and packaging formats. Line changeovers are performed by CIP, clean-in-place cycles, product purges, and recipe uploads via the SCADA interface. Automated valves and sensor diagnostics reduce downtime between batches. Lines may produce up to 8,000 liters of finished sorbet per hour, depending on viscosity, inclusion complexity, and packaging speed. Nutella biscuits manufacturing begins with production of the biscuit shell using a rotary molding and baking process. The biscuit dough is prepared by blending wheat flour with vegetable fats and powdered sugar inside a continuous horizontal mixer. The mixer operates at fixed low speed to prevent gluten development while ensuring even dispersion of fat particles across the flour. Water is added near the end of the cycle to activate binding. The dough is mixed until it reaches a defined plasticity suitable for molding and is then discharged into a feeding hopper connected to the forming line. The rotary molder presses the dough into engraved cavities on a rotating drum. The cavities have an open bottom design to release formed biscuits onto a steel mesh conveyor belt. The upper roller applies pressure to ensure full cavity fill, while the scraper removes excess dough and reintroduces it into the system. Each molded shell includes a circular depression designed to receive the Nutella filling after baking. The unbaked shells are spaced at regular intervals on the conveyor to allow for controlled baking conditions. The biscuit shells are conveyed into a multi-zone tunnel oven for baking. The tunnel consists of top and bottom heating elements, independently controlled in each zone. The oven temperature rises gradually from 160 to 210 degrees Celsius across the length of the tunnel. The baking profile is optimized to achieve full moisture removal from the dough without causing expansion or deformation of the molded cavity. Residence time in the oven is calibrated to match dough moisture content and thickness. Shells exit the oven fully baked with crisp structure and low residual humidity. After baking, the biscuit shells are cooled using ambient air directed across multiple conveyors arranged in a serpentine path to reduce surface and internal temperatures evenly. Cooling is required to stabilize the biscuit structure and prepare the cavity for Nutella filling. The biscuits are held at rest until their surface temperature falls below 30 degrees Celsius to prevent filling separation. In parallel, the Nutella filling is prepared in a high-shear emulsification unit. Using sugar, skimmed milk powder, cocoa, hazelnut paste, and vegetable oils. The ingredients are pre-mixed in separate feeders and metered into a blending vessel. The vessel operates under vacuum to remove entrapped air and maintain smooth consistency. The filling is processed at controlled temperature of 40 to 45 degrees Celsius to keep the viscosity within a defined range suitable for extrusion. Once homogenized, the filling is pumped to a filling head fitted with multiple nozzles. The cooled biscuit shells are conveyed under the filling head where each cavity is aligned with a single nozzle. A volumetric piston system injects the Nutella filling into each cavity with precise volume control. The fill level is calibrated to rise just below the edge of the biscuit wall to allow sealing with the top biscuit layer. After filling, the open surface is inspected for overflow or inconsistency using machine vision systems that communicate with rejection gates for off-spec product. A second biscuit layer is prepared using a similar dough mixing and molding process, but with a flat profile and no cavity. These flat biscuits are baked and cooled on a parallel line. After cooling, they are conveyed to the sandwiching station, where they are aligned and placed on top of the filled biscuit shells. Robotic arms or mechanical pushers perform the alignment and placement. Each top biscuit is pressed gently to create full contact with the Nutella surface, ensuring mechanical bonding through surface tension of the fat-based filling. The sandwich biscuits enter a brief setting tunnel where cool air is applied to solidify the outer edges of the filling. This step reduces movement during handling and packaging. The biscuits exit the tunnel with the Nutella core enclosed between two baked shells. Completed Nutella biscuits are conveyed to a wrapping line. Each biscuit is separated by timing belts and transferred to a horizontal flow wrapping machine. Printed film is pulled from a roll and formed into a tube by a forming collar. The biscuit enters the tube, and the machine applies a longitudinal heat seal using rotating pressure rollers. End seals are created using heated sealing jaws that cut and close the wrapper simultaneously. Wrapped units are transferred to a grouping station where multiple biscuits are oriented into lanes and grouped for final packaging. Mechanical pushers move the groups into pre-formed trays or cartons, which are closed and sealed using hot melt glue. Cartons are held under compression for a fixed time to ensure glue adhesion before being moved to the final packing area. Each element of the Nutella biscuit structure is formed in distinct production zones that operate in parallel and converge during assembly. The biscuit shell relies on controlled dough plasticity, consistent cavity shaping, and uniform baking to maintain its geometry. The filling requires stable emulsification and thermal regulation to maintain deposition quality and shelf stability. Assembly depends on mechanical alignment, volumetric precision, and sealing reliability. Material flow through the plant is linear, with dedicated conveyance systems connecting each station. Biscuit shells and tops are kept on separate synchronized lines to ensure timing consistency during sandwiching. The filling pump rate and nozzle actuation are matched to biscuit speed to maintain throughput. Each station includes real-time sensors to monitor dough consistency, bake color, biscuit thickness, fill weight, and seal integrity. These sensors feed data to a central programmable logic controller that adjusts line speed, pump rate, and heating elements based on tolerances. The manufacturing of Nutella biscuits depends entirely on coordinated dosing, shaping, heating, cooling, filling, sealing, and wrapping processes. Every stage transforms the materials physically by temperature or mechanical force, without the use of molding or batch processing beyond the initial dough and filling prep. All thermal zones are closed-loop systems with adjustable airflow and temperature feedback. Air velocity, humidity, and direction are optimized to control baking profiles and cooling rates. These variables determine final texture and filling retention. Filling viscosity is adjusted by temperature control and shear rate. The shear thinning nature of the filling allows fast deposition while maintaining form when static. Deposit shape is retained until enclosed by the top biscuit and set during the cooling phase. Final product dimensions are defined by the cavity shape of the rotary mold and the flatness of the sealing biscuit. Mechanical indexing ensures positional accuracy for every fill and seal. No lateral shift is tolerated at the sealing station. The top biscuit must be seated with uniform pressure to prevent leakage or deformation. This step is controlled by pneumatic actuators that apply force within a calibrated range to prevent structural damage to the shell. The flat biscuit must align concentrically with the base. All scrap or off-spec products are diverted to return belts for reprocessing or rejection. These include unfilled shells, misaligned sandwiches, overfilled units, and wrapping errors. Each rejection path is physically separated to maintain uninterrupted flow of conforming units. Finished wrapped units pass a final weight check and metal detection station before secondary packaging. Cartons are printed, coded, sealed, and stacked for dispatch. No rework is conducted beyond primary quality rejection zones. Oreo production starts with the preparation of the chocolate biscuit dough using a high-capacity continuous mixer. Dry ingredients including soft wheat, flour, sugar, cocoa powder, and leavening agents are first weighed and fed into the mixing chamber. A separate line introduces palm oil or shortening, which is preheated to maintain fluidity and evenly distributed across the dry blend. Water is added gradually to initiate dough formation while mixing paddles rotate at low speed to prevent overdevelopment of gluten. The process continues until the dough reaches uniform consistency with defined plasticity suited for rotary molding. The mixed dough is conveyed to the forming system via an auger feed mechanism. The dough enters the hopper of a rotary molder, equipped with engraved rollers that define the embossed biscuit design. As the dough passes through the rollers, it is pressed into the cavities with precise pressure and then released onto a wire mesh baking band by means of a stripping knife. Excess dough is scraped from the roller surface and returned to the feed hopper for reuse. Biscuits are formed in continuous rows and spaced evenly to allow thermal exposure during baking. The molded biscuit pieces are carried into a multi-zone tunnel oven. The baking process is divided into sequential zones where temperature and air velocity are independently controlled. The oven begins at a moderate heat to set biscuit shape and rises to higher temperatures to complete internal baking and develop surface color. The typical baking curve ranges from 160 to 220 degrees Celsius. Each biscuit remains in the oven for 6 to 9 minutes, depending on thickness and moisture content. The mesh band allows uniform exposure to heated air on all sides. After baking, the biscuits are discharged onto a cooling conveyor where ambient air is directed from above and below to bring the temperature down gradually. The biscuits move across multiple levels or loops of conveyors to extend cooling time without occupying additional floor space. Final biscuit temperature is reduced to below 30 degrees Celsius to ensure structural stability before sandwiching. Simultaneously, the creme filling is prepared in a separate emulsification line. The filling consists of icing sugar, hydrogenated vegetable oil, soy lecithin, and flavoring agents. Ingredients are loaded into a planetary mixer equipped with high-speed blades and jacketed walls. The sugar is ground and combined with oil under shear to produce a smooth, homogeneous, fat-based paste. Temperature is maintained between 35 and 40 degrees Celsius to control viscosity and ensure pumpability. Once mixed, the filling is transferred to a holding tank fitted with agitators to prevent settling or phase separation. The cooled biscuits are conveyed into the sandwiching station in a synchronized line. They are separated into top and bottom rows using mechanical diverters. The bottom biscuits move directly under the filling depositor, while the top biscuits follow a delayed path to allow time for the filling application. The depositor contains multiple nozzles aligned with each lane of biscuits. Each nozzle dispenses a fixed volume of cream using a positive displacement piston pump. The deposit is placed at the center of each biscuit with consistent diameter and height. Top biscuits are aligned and placed onto the filled base biscuits by a pick and place mechanism. A servo-controlled arm picks the top halves and lowers them precisely onto the creme layer. The contact pressure is adjusted to spread the filling evenly without causing overflow. The result is a sandwich structure with a defined creme layer held between two embossed chocolate biscuits. Each finished sandwich is inspected for alignment and fill consistency using vision sensors and rejected automatically if outside tolerance. Sandwiched Oreos are then conveyed to the packaging section. The product flow is timed to match the entry speed of the horizontal flow wrapping machine. Wrapping film is unrolled and passed through a former to create a continuous tube. The Oreos enter the tube and are enclosed longitudinally using heated crimp rollers. Transverse end seals are applied using rotating sealing jaws that cut and seal each package simultaneously. Seal parameters are adjusted for film thickness and product temperature. The wrapped Oreos exit the machine in a sealed pillow pack configuration. Multiple wrapped packs are grouped into secondary packaging units using collection conveyors and counting gates. Depending on the product format, they may be stacked or aligned edge to edge and loaded into pre-formed cartons. Cartons are formed from flat blanks using folding arms and sealed with hot melt glue. Filled cartons are compressed briefly to ensure adhesive bond and discharged onto the final conveyor. Each line operates continuously and is monitored by sensors that track biscuit position, deposit weight, package seal integrity, and material usage. The entire process is controlled by a centralized PLC system that coordinates line speed, temperature settings, pump pressures, and mechanical alignment across all stages. Biscuit texture is determined by dough moisture content, oven temperature profile, and baking time. Creme consistency is controlled through oil phase properties, shear rate, and deposition temperature. Assembly quality is a function of alignment precision, deposit accuracy, and pressure applied during sandwiching. Packaging integrity depends on film properties, sealing jaw temperature, and dwell time. Throughout Oreo production, no stage is batch-based beyond initial mixing. Dough and creme preparation feed into continuous mechanical systems that deposit, shape, bake, cool, fill, and wrap in a single linear sequence. Ingredient transformation is physical through heating, mixing, and compression. Structural integrity is achieved by thermal setting in the oven and mechanical bonding during sandwiching. The shape and weight of each Oreo are determined by the engraved mold cavities and the metered deposit volume. The embossed pattern is preserved by controlled dough texture and low expansion during baking. Biscuit brittleness is managed by adjusting water content and baking duration. Fill height is maintained by calibrating piston stroke length and pump cycle frequency. Every motion in the line contributes to dimensional uniformity and output consistency. Dough movement is regulated by roller speed and auger feed rate. Biscuit placement is defined by indexing and lane spacing. Creme application depends on nozzle diameter and internal deposit pressure. Sandwich closure requires precise Z-axis movement and timed application force. The rotary molding drum is cleaned automatically using scraper blades and air jets between production runs. Dough formulation is adjusted in real time based on humidity and flour batch variation. Viscosity of the creme filling is monitored using inline viscometers that signal temperature adjustments in the holding tank jacket. Oven parameters are logged continuously and used to regulate the baking curve. The production of Oreo cookies involves multiple heat and shear-based unit operations that alter physical properties without any fermentation or leavening beyond minor chemical agents. All dimensions are mechanically imposed and retained by careful control of thermal transitions and compression events. No rework is introduced into the sandwiching process. Only biscuits that meet shape, color, and thickness criteria are accepted. Filling rejects are filtered back into the holding tank through a return line. Packaging errors are removed before sealing to prevent final product contamination. The system is designed to maintain flow and reject outliers without stopping. The final Oreo structure consists of 2 rigid outer shells and 1 malleable creme layer. The shells resist deformation under handling. The creme adheres without fluid migration. Moisture barrier properties are maintained by the biscuit's low water activity and the hydrophobic nature of the fat-based filling. Nutter butter cookie production begins with the preparation of the peanut-flavored dough. Dry base materials are loaded into a large capacity horizontal mixer through automated dosing systems. These materials include soft wheat flour, granulated sugar, dextrose, baking soda, salt, and peanut flour. Separately, hydrogenated vegetable oil and peanut butter are preheated in jacketed holding tanks to reach a flowable state. The fats are pumped into the mixer and distributed over the dry mix, while the paddles rotate at low speed. Water is then injected into the chamber through spray nozzles to activate hydration without overdeveloping gluten. Dough temperature is maintained between 18 and 22 degrees Celsius. The dough is mixed until a target plasticity is achieved, ensuring it can be molded without sticking or tearing. Once complete, the dough exits the mixer via a discharge chute and is conveyed to a dough feed hopper mounted above a rotary molder. The molder is equipped with engraved rollers featuring the signature peanut shell pattern and split mold design that will define the top and bottom cookie pieces of the Nutter Butter sandwich. As the dough is fed into the rotary molder, the engraved drum compresses and shapes the dough into uniform cookie halves. A fixed scraper blade removes excess dough from the roller's surface, while a vacuum-assisted mechanism ensures accurate demolding from the cavities. formed cookies are transferred onto a wire mesh conveyor belt that transports them through a continuous tunnel oven. Excess dough is rerouted via a return auger and refed into the forming system. The tunnel oven is divided into sequential thermal zones with independent temperature control. The initial zone sets the cookie shape at approximately 160 degrees Celsius. The intermediate zones raise temperature to 200 degrees Celsius to drive off internal moisture. The final zone applies finishing heat at 220 degrees Celsius to develop the surface texture and light browning. Airflow direction and volume are adjusted separately for top and bottom heating across all zones. The wire mesh belt permits full convection exposure around each cookie piece. Total baking time ranges from 6 to 9 minutes depending on dough moisture, product thickness, and belt speed. During baking, moisture content is reduced from around 18% to below 2%. The cookies exit the oven fully formed and structurally rigid. They are conveyed to an ambient cooling system composed of multi-tiered belts with forced air circulation. Cookies must reach below 30 degrees Celsius before proceeding to filling. While the cookies cool, the peanut butter creme filling is produced in a separate, continuous emulsification system. The formulation includes icing sugar, hydrogenated vegetable oil, roasted peanut paste, salt, and emulsifiers such as mono and diglycerides. The ingredients are metered into a vacuum mixer fitted with high-speed rotating blades. The mixer maintains low pressure to prevent air incorporation, while the fat and sugar blend into a smooth paste. Product temperature is held between 38 degrees Celsius and 42 degrees Celsius to control viscosity and ensure deposit stability. The filling mass is pumped from the mixer into a stainless steel holding tank equipped with a slow agitator to maintain consistency. From there, the creme is fed through a positive displacement pump into a volumetric depositor that sits above the sandwiching conveyor. Cooled cookie halves are divided into bottom and top rows using a mechanical separator with indexed belts. The bottom halves are aligned and conveyed beneath the depositor. Each nozzle in the depositor corresponds to one cookie lane. As each cookie passes below, a metered quantity of peanut creme is dispensed onto the center of the bottom cookie surface. The deposit rate is synchronized with belt speed to maintain consistent fill weight and location. Top cookie pieces are then aligned with their corresponding filled bottom halves using a mechanical alignment rail. A pusher bar or servo-driven actuator lowers each top cookie onto the filling. The applied pressure is controlled to spread the filling to the desired diameter without squeezing it beyond the edge. The resulting sandwich maintains clean fill lines and full bonding across the contact surface. Assembled Nutter Butter sandwiches are conveyed through a short resting belt to allow any residual filling movement to stabilize. From there, they move into the packaging system. The first packaging stage consists of a flow wrapping machine fed by a timing belt that spaces cookies at fixed intervals. Wrapping film is unwound from large rolls and formed into a tube around the cookies using a forming collar. The longitudinal seam of the wrapper is sealed by heated crimp rollers, while the ends are cut and sealed by rotary jaws. Temperature and dwell time of the sealing jaws are set based on film thickness and line speed. The wrapped cookies exit the flow wrapper as individual units or twin packs depending on the product variant. Wrapped units are conveyed to a grouping system where multiple cookies are collected and inserted into multi-pack cartons. Mechanical pushers or robotic pick-and-place arms load the cookies into pre-glued cartons. Cartons are sealed using hot melt adhesive applied by contact nozzles. Glue setting is ensured by compression flaps and a short dwell section. The cartons are then labeled, coded, and discharged to case packing. Throughout the process, all movements are continuous and synchronized. Dough feed, forming, baking, cooling, creme preparation, depositing, sandwiching, and wrapping occur without manual intervention or batch holding. Each station is linked to upstream and downstream processes by belt conveyors, sensor arrays, and real-time control systems. The final texture of the Nutter Butter cookie shell depends on dough fat content, moisture level, forming pressure, and thermal profile. The filling spread and adhesion characteristics are governed by shear during mixing, fat phase structure, and filling temperature at deposition. The sandwiching step relies on timing and vertical alignment accuracy to avoid rotation or breakage. Rework is minimized through inline inspection at multiple points. Cookies with incomplete molding, overbake, off-center filling, or misalignment are removed by air rejection systems or diverted for grinding and remelting. Only fully conformed products proceed to final packaging. The design of the peanut shell shape is retained through rigid cavity molding, low dough expansion, and short baking time. Each cavity in the mold drum is precision machined to micron level tolerances. The emboss pattern depth controls final surface visibility. The moisture balance in the dough ensures sharp edge retention and minimal slumping during oven transit. The filling deposit pattern is a function of nozzle diameter, piston stroke length, deposit speed, and creme viscosity. The diameter of the final fill is determined by vertical pressure from the top cookie and the flow behavior of the fat matrix. The ratio between shell weight and filling weight is maintained within narrow limits to ensure structural integrity and mouthfeel. Line efficiency is governed by synchronization between forming rate, baking throughput, and filling capacity. Adjustments to belt speed, oven temperature, or depositor cycle timing propagate downstream. Any mismatch between stations can result in underbake, inconsistent fill, or packaging misfeeds. The mechanical layout of the Nutter Butter production line is linear and modular. Dough flows from mixer to molder. Biscuits flow from molder to oven. Creme flows from mixer to depositor. Sandwiches flow from depositor to wrapper. Each segment includes buffer zones to absorb variation and maintain steady output. Packaging formats can be switched by adjusting forming jaws, wrapping film feed width, and carton loader configuration. Line reconfiguration is managed through digital interfaces that adjust motion profiles, material flow paths, and spacing intervals. The final Nutter Butter product consists of 2 molded peanut-flavored cookies bonded with a central layer of smooth peanut butter creme. The top and bottom shells are symmetrical and embossed with the same pattern. The cream layer is centered and flush with the cookie edge. The finished unit exhibits uniform thickness, aligned sandwich halves, and sealed packaging with fixed weight. Each unit operation transforms the ingredients through shear, heat, pressure, cooling, or extrusion. No fermentation or chemical expansion occurs. All structural characteristics are mechanically imposed and thermally locked. The line operates at a continuous pace of thousands of cookies per hour. Consistency across units is maintained by regulating every input condition, from ingredient feed to forming pressure to deposit rate. All cookies follow the same linear path through the same physical conditions. The result is a uniform, mass-produced sandwich product with no variation in shape, weight, or filling distribution. Fresh strawberries arrive in bulk containers and are immediately transferred onto vibrating sorting tables. The surface trembles in rapid pulses, spreading the fruit into a single layer. Optical scanners sweep across the moving belt, detecting color density and surface irregularities. Jets of compressed air fire in milliseconds, ejecting underripe or bruised berries. The selected strawberries continue forward in a uniform stream. The fruit drops into a rotating drum washer. High-pressure sprays strike from multiple angles, stripping away soil and field residue. The drum slowly turns, ensuring every surface is exposed to the water jets. Excess water drains through perforations while the berries advance toward the discharge chute. A final mist rinse removes remaining particles before the fruit exits onto a dewatering conveyor lined with absorbent rollers. Next, the strawberries pass beneath stainless steel blades that remove stems with precise vertical cuts. The trimmed berries fall into a stainless hopper feeding an industrial crusher. Inside the crusher, rotating paddles press the fruit against a perforated screen. The flesh collapses into a thick pulp, releasing juice and seeds. The sound shifts from a soft tumble to a wet grinding hum as the texture transforms into a uniform mash. The pulp moves into a heated processing tank equipped with a slow-turning agitator. Granulated sugar is metered in through a screw feeder. The agitator sweeps through the mixture, dissolving sugar crystals into the strawberry mass. Gentle heat intensifies the aroma while evaporating excess moisture. The mixture thickens slightly as soluble solids increase. A refractometer probe continuously measures sugar concentration, adjusting feed rates to reach precise sweetness. Once balanced, the strawberry blend flows through a fine mesh filter. Seeds and fibrous fragments are separated, producing a smooth puree. The filtered puree enters a vacuum deaerator, where trapped air bubbles rise and collapse under reduced pressure. The surface briefly foams, then settles into a glossy, uniform liquid. This step prevents oxidation and preserves the bright red hue. Parallel to fruit preparation, the dairy base begins in large insulated tanks. Fresh cream and whole milk are pumped in controlled proportions through stainless pipelines. Load cells beneath the tanks monitor weight to ensure exact ratios. Liquid sugar syrup joins the blend through automated valves, eliminating undissolved crystals. The mixture swirls under high-speed agitators, forming a homogeneous liquid. Milk solids and stabilizers are introduced through a powder induction system. Fine. Powders are drawn into the vortex created by the spinning mixer, preventing clumping. The stabilizers hydrate gradually, thickening the base and improving body. The sound of the mixer deepens as viscosity increases. Temperature sensors regulate the mixture to maintain optimal hydration conditions. The blended dairy base is pumped into a plate heat exchanger for pasteurization. Thin layers of liquid flow between heated stainless plates. Hot water circulates on the opposite side, raising the temperature rapidly. The mixture reaches pasteurization temperature within seconds and is held briefly in a holding tube. This precise thermal treatment eliminates unwanted microorganisms while preserving flavor integrity. Immediately after heating, the mixture travels back through the heat exchanger, where chilled water cools it down quickly. The rapid drop in temperature prevents overcooking. The base exits at a cold, controlled temperature and flows into aging tanks. Inside these tanks, slow, paddles rotate gently, preventing separation while allowing fat molecules and proteins to stabilize. Over several hours, the mixture thickens slightly as fat crystallizes and stabilizers fully hydrate. Once aged, the dairy base is directed toward a high-pressure homogenizer. The liquid is forced through microscopic openings under intense pressure. Fat globules shatter into tiny droplets, dispersing evenly throughout the mixture. The texture becomes smoother and more stable. The transformation is audible as a sharp hiss accompanies the sudden pressure release. The homogenized base and the prepared strawberry puree converge in a blending tank. Automated flow meters synchronize their entry to achieve the desired fruit concentration. As they merge, rotating blades fold the red puree into the pale dairy liquid. The color shifts from off-white to a uniform pink. The mixture thickens slightly as fruit solids integrate with the cream structure. The combined mixture flows into a continuous ice cream freezer. Inside the cylindrical freezing barrel, refrigerant circulates around the outer shell, drawing heat away rapidly. A dasher spins within the barrel, scraping frozen layers from the inner wall. The scraping action prevents large ice crystals from forming. Simultaneously, controlled air is injected into the mixture. Tiny air bubbles disperse evenly, increasing volume and creating a light texture. As the mixture churns, it transforms from liquid to semi-solid. The texture resembles soft snow. Temperature probes monitor the freezing point continuously. The dasher blades slice through the thickening mass with rhythmic precision, producing a steady mechanical hum. Within minutes, the ice cream reaches a soft serve consistency and is extruded from the barrel through a nozzle. For varieties containing strawberry pieces, an inclusion feeder introduces diced fruit at this stage. The small cubes drop into the flowing stream and are folded gently by a low-speed auger. The movement distributes the pieces evenly without crushing them. Bright fragments remain suspended in the creamy matrix. The semi-frozen ice cream moves through insulated pipes into filling machines. Containers travel along a conveyor beneath multi-nozzle fillers. Each nozzle descends and releases a measured volume. The soft ice cream spirals into the container, forming layered folds. Vibrating plates beneath the conveyor remove trapped air pockets and level the surface. Lids are placed automatically by a rotary placer. A brief downward press seals each container. Date codes are printed in precise black ink on the lid surface. The filled units advance into a hardening tunnel. Inside, powerful fans blast air at extremely low temperatures. The air circulates at high velocity, stripping remaining heat from the product. During hardening, ice crystals stabilize into a fine structure. The temperature at the core drops steadily until the entire mass becomes firm. The transformation locks in the overrun and prevents structural collapse. The containers exit the tunnel solid and rigid. They pass through a metal detection system that scans each unit for metallic fragments. A reject arm removes any container that fails the scan. Approved units continue to a cartoning station where multiple containers are grouped and wrapped in printed sleeves. Mechanical arms fold cardboard around the stack with crisp, angular movements. The cartons move onto a palletizing line. Robotic arms lift entire layers and stack them with geometric precision. Each layer aligns perfectly, forming a stable cube. Stretch film wraps tightly around the stacked load, binding it into a single secure mass. Before storage, samples from each batch are tested in a texture analyzer. A probe presses into the frozen ice cream, measuring resistance and consistency. The data confirms proper freezing and air incorporation. Color sensors verify uniform pink tones, ensuring the strawberry dispersion is consistent. Throughout the entire process, stainless steel pipelines connect every stage. Pumps pulse rhythmically, maintaining continuous flow. Valves open and close in timed sequences controlled by automated systems. Digital panels display temperatures, pressures, and flow rates in real time. Each transformation occurs in a precise order, from raw fruit and liquid dairy to aerated frozen structure. The final packaged strawberry ice cream rests in cold storage at stable sub-zero temperatures. Inside each sealed container, microscopic ice crystals, evenly distributed air cells, stabilized fat droplets, dissolved sugars, and concentrated strawberry solids form a balanced matrix. The journey from whole berries and fresh cream to smooth frozen dessert is defined entirely by controlled motion, measured heat exchange, rapid freezing, and exact mechanical coordination. Raw milk is delivered to the processing facility in insulated stainless steel tanks. Upon arrival, the milk is passed through a series of mesh strainers to remove any large particulate matter. It then flows into a balance tank, where load cells continuously measure the volume and ensure accurate downstream processing. The temperature of the milk is monitored by inline thermocouples, confirming it is within a range suitable for further processing. The milk proceeds to a clarification step. High-speed centrifuges spin at thousands of revolutions per minute, using centrifugal force to separate any remaining somatic cells, small debris, or micro-impurities. Clarified milk exits the centrifuge through a continuous discharge system, maintaining a smooth, consistent flow. The removal of these particles ensures uniformity in subsequent heating and fermentation stages. Next, the milk enters a standardization phase. Skim and cream fractions, measured precisely by flow meters, are blended to achieve the desired fat content for Greek yogurt. The mixture passes through automated mixers that homogenize the dairy liquid, dispersing fat droplets uniformly to prevent separation and ensure a smooth, final texture. Homogenization is critical for creating a thick, creamy mouthfeel after fermentation and straining. The standardized milk then undergoes pasteurization. It flows through a plate heat exchanger, where thin layers of milk pass between heated stainless steel plates. Hot water, or steam, circulates on the opposite side, rapidly raising the temperature to a controlled level, typically around 85 to 90 degrees Celsius. The milk is held at this temperature in a holding tube for several seconds to destroy pathogenic bacteria and deactivate enzymes. Pasteurization ensures safety and stabilizes proteins for improved coagulation. Immediately after pasteurization, the milk is cooled rapidly via the same heat exchanger in counterflow, using chilled water or glycol to bring it down to the fermentation temperature, typically around 42 to 45 degrees Celsius. Rapid cooling prevents overcooking the proteins and preserves a neutral flavor profile, readying the milk for bacterial culture inoculation. The milk then flows into fermentation tanks. Starter cultures containing specific strains of Lactobacillus bulgaricus and Streptococcus thermophilus are introduced in measured doses. Automated dosing systems ensure exact quantities of active cultures are dispersed evenly. The milk is gently agitated to distribute the bacteria uniformly without creating excessive air bubbles, which could interfere with texture development. Fermentation begins as the tank is held at controlled temperature. Heating jackets or circulating water jackets maintain constant warmth. The bacteria metabolize lactose into lactic acid, gradually lowering the pH of the milk. As acidity increases, casein proteins destabilize and aggregate, forming a gel network. The process is monitored via inline pH sensors, which track the decrease in pH toward the target range, typically between 4.5 and 4.6. During fermentation, slow, intermittent stirring ensures uniform heat distribution and prevents a dense skin from forming on the surface. The gel forms gradually, transforming the liquid milk into a soft, viscous curd. The curd's elasticity is assessed through viscometers or occasional manual sampling to determine the readiness for straining. After the curd reaches the desired acidity and consistency, fermentation ceases by cooling. The tanks are chilled using recirculated cold water or brine jackets, rapidly bringing the yogurt to around 4 degrees Celsius. Cooling halts bacterial activity, stabilizes the gel network, and prevents over-acidification. The cooled yogurt now has a creamy, spoonable texture, but is still high in whey content compared to traditional Greek yogurt. The next stage is straining, which is critical to producing Greek yogurt's characteristic thickness. The yogurt is pumped into centrifugal separators or stainless steel sieves equipped with fine mesh filters. Mechanical pressure or centrifugal force separates liquid whey from the solid curd. In some systems, vacuum-assisted filtration accelerates whey removal while maintaining the integrity of the protein matrix. The result is a dense, creamy yogurt with concentrated milk solids. For large-scale production, the strained yogurt may pass through multiple sequential centrifuges or filters to achieve the target consistency. Each stage incrementally removes whey, reducing moisture content and increasing protein concentration. The sound of liquid passing through perforated plates and the gentle hum of centrifugal rotors indicate continuous separation. Monitoring instruments track moisture levels and protein content to ensure consistency batch to batch. After straining, the thickened yogurt may be blended briefly to homogenize texture. Low shear paddle mixers fold the curd gently, eliminating pockets of firmer or looser gel while avoiding aeration that could introduce unwanted air bubbles. The texture at this point is dense but smooth, with a uniform pale white color. If flavoring or fruit inclusions are desired, they are introduced in a separate blending stage. Natural fruit purees, syrups, or flavor extracts are metered into the thick yogurt using precision dosing pumps. Rotating augers fold these additives gently, maintaining the yogurt's viscosity while achieving even distribution. Inline mixing sensors ensure consistent blending without breaking the gel network. The yogurt then moves to filling equipment. Containers travel along conveyors beneath precision nozzles that deposit exact volumes. The yogurt flows in a continuous stream or spirals into the containers, forming a smooth surface. Vibrating platforms may gently level the yogurt and remove trapped air bubbles, preventing voids that could affect shelf appearance and texture. Filled containers pass through automated capping systems. Lids are sealed with controlled pressure, ensuring airtight closure. Date coding machines print batch information directly on the lid surface. The sealed units are then conveyed into cold storage chambers. Rapid cooling continues as the yogurt is brought down to storage temperature, typically around 0 to 4 degrees Celsius. This step further stabilizes texture, slows bacterial activity to preserve shelf life, and maintains product integrity during handling. Temperature-controlled conveyors and chill tunnels ensure minimal fluctuation, maintaining the thick, creamy structure of the Greek yogurt. Throughout the production line, stainless steel pipelines connect tanks, filters, and filling machines. Pumps regulate flow rate, while automated valves open and close in precise sequences. Sensors continuously monitor flow, temperature, pH, and protein content, providing real-time data to the control system. Any deviation triggers adjustments to maintain consistent product quality. During quality control, samples are drawn from various points along the line. Rheometers measure viscosity, ensuring the yogurt meets textural specifications. Moisture analyzers confirm the whey content aligns with Greek yogurt standards. Colorimeters check for uniformity in hue and brightness. Microbiological tests verify that bacterial counts are within acceptable ranges, confirming proper fermentation and pasteurization effectiveness. The final product exhibits a dense, creamy texture with minimal whey separation. Protein concentration is high, a result of controlled straining and careful homogenization. The yogurt retains a subtle tang from lactic acid development and, if included, uniform fruit dispersion or flavor infusion. Containers are stacked and wrapped for storage, ready to maintain their structure until distribution. Robotic palletizers lift layers of containers and stack them with precise alignment. Stretch film wraps the pallet, securing it for cold transport. Throughout handling, the Greek yogurt remains chilled, preventing separation or texture degradation. Each pallet holds hundreds of containers, reflecting the cumulative precision of pasteurization, fermentation, straining, blending, and packaging. Every stage of the process emphasizes mechanical control and precision. From raw milk clarification through homogenization, controlled fermentation, whey removal, and final packaging, the production relies on continuous monitoring of temperature, pH, viscosity, and moisture. The interplay of mechanical devices, centrifuges, mixers, heat exchangers, pumps, and filling machines ensures consistency, texture, and protein concentration in every batch. The journey from liquid milk to thick, creamy Greek yogurt is defined by sequential transformations: purification, fat standardization, heat-induced protein denaturation, bacterial fermentation, gel formation, controlled cooling, whey separation, and gentle blending. Each transformation is quantified and monitored, producing a stable, high-protein yogurt with characteristic density and smoothness. Even at microscopic scale, the structure is precise. Fat. Droplets are homogenized and dispersed. Protein networks form consistent matrices, and tiny air pockets are minimized. Whey removal concentrates solids without fracturing the gel. The final yogurt exhibits uniform texture, flavor, and acidity due entirely to controlled mechanical and thermal processes. Mascarpone cheese arrives in insulated tanks and is first examined for temperature and consistency. The cheese is pumped through stainless steel pipelines into a blending vat. High shear agitators rotate within the vat, dispersing the dense cheese uniformly and ensuring no lumps remain. The mixers are equipped with variable speed motors, allowing precise control of shear forces to maintain the creamy texture without aerating excessively. Load cells beneath the vat monitor the mass of cheese entering the mixer to confirm exact quantities for recipe consistency. Egg yolks are separated mechanically using rotary egg breaking machines. The eggs are cracked, and yolks and whites are divided using centrifugal separators. Yolks are collected in stainless steel hoppers and gently pumped to pre-blending tanks. Inline viscometers monitor the viscosity of the yolk stream, ensuring smooth, homogeneous flow before incorporation. Sugar is introduced via screw feeders, passing through heated hoppers to prevent clumping. Paddle agitators fold the sugar into the yolks gradually, allowing partial dissolution and formation of a light, smooth custard base. The mascarpone is folded into the yolk-sugar mixture using low-speed planetary mixers. Rotating arms sweep through the mixture, gently folding the dense cheese into the custard without incorporating air. Sensors track torque on the mixer shafts, providing data on viscosity progression. Once fully integrated, the mixture has a uniform, glossy appearance and a controlled thickness that will later allow it to layer effectively in the final dessert. Separately, espresso coffee is brewed continuously. Water is pumped into high-pressure stainless steel extraction units at precisely 92 to 95 degrees Celsius. Ground coffee is metered into portafilters or drum roasters, compacted by mechanical tampers. Pressurized water flows through the grounds at a controlled rate, extracting soluble solids and aromatic compounds efficiently. The resulting espresso flows into holding tanks equipped with heat jackets to maintain temperature until required for soaking. A continuous conveyor system moves the espresso from brewing to the soaking station with minimal exposure to air, preserving flavor integrity. Optional liqueurs, such as coffee-flavored or almond-based spirits, are stored in temperature-controlled tanks. Flow meters regulate the addition of liqueur to the espresso in mixing tanks. Static mixers create a homogeneous coffee liqueur blend, maintaining precise flavor ratios. The mixture passes through inline thermometers, ensuring it is at a temperature that will saturate the ladyfinger biscuits without prematurely softening them. Ladyfinger biscuits are produced separately. Flour, sugar, eggs, and leavening agents are combined in a high-speed mixing ribbon or planetary mixer. The batter's viscosity is monitored by inline rheometers to ensure it is thick yet pourable. Once mixed, the batter is extruded through nozzle systems onto conveyor belts in uniform finger shapes. The fingers pass through tunnel ovens with controlled zones of convection and infrared heating, baking them to a firm yet spongy consistency. Cooling conveyors allow the biscuits to reach ambient temperature while retaining flexibility for soaking. The cooled ladyfingers are transferred to an automated soaking line. Conveyors align the biscuits in single layers beneath nozzles that dispense measured volumes of coffee liqueur mixture. The liquid jets impact the biscuit surface precisely, soaking the exterior without disintegration. Vibrating trays under the nozzles gently shake the biscuits, promoting uniform absorption. Sensors track moisture content in real time, adjusting nozzle flow rates and conveyor speed to achieve consistent saturation across all units. After soaking, the biscuits are deposited into filling trays by robotic arms or gravity-fed systems. The trays are designed with cavities corresponding to the final product size. Each cavity receives a layer of soaked ladyfingers, forming the base layer of the tiramisu. Sensors confirm correct placement, detecting misaligned or broken biscuits, which are automatically removed from the line. The mascarpone yolk sugar mixture is then transferred to depositing machines. Multi-nozzle filling heads extrude precise amounts over the biscuit base. Linear actuators and programmable logic controllers coordinate nozzle motion to spread the mixture evenly. Low-speed paddles may be used after deposition to smooth the layer without incorporating air, preserving the dense, creamy texture characteristic of tiramisu. If multiple layers are required, the process repeats. Another layer of soaked ladyfingers is added atop the mascarpone layer, followed by additional cheese mixture deposition. Robotic arms and precision conveyors ensure exact alignment of layers, avoiding displacement or uneven thickness. Inline laser sensors monitor height and uniformity across the tray, signaling adjustments in deposition volumes to maintain consistency batch to batch. Cocoa powder application occurs once all layers are complete. Fine mesh sifters deliver a controlled dusting of cocoa over the surface. Pneumatic shakers or vibrating plates assist in evenly distributing the powder, preventing clumping or excessive coverage. In large-scale production, automated dispensing heads move across the tray to maintain a uniform layer of cocoa, forming the characteristic top finish of the tiramisu. Color sensors verify the evenness and intensity of the cocoa layer. Completed trays proceed to refrigeration tunnels. Cold air circulates at high velocity, rapidly bringing the product down to approximately 4 degrees Celsius. The cooling process is gradual enough to preserve the gel structure of the mascarpone layer, but fast enough to stabilize moisture in the ladyfingers. Fans and airflow deflectors maintain uniform temperatures across trays, preventing condensation or uneven chilling. During storage and transport, trays remain in temperature-controlled environments. Sensors monitor core temperatures to ensure the mascarpone mixture remains firm without freezing. Refrigerated conveyors maintain orientation and prevent tilting, which could disrupt layered structure. Shock-absorbing supports minimize vibrations, preserving the integrity of delicate layers during handling. Before packaging, automated vision systems inspect each tray. Cameras detect layer uniformity, surface smoothness, and cocoa distribution. Deviations beyond preset tolerances trigger removal or correction of the tray. This ensures that the visual appearance aligns with specifications. Weight sensors confirm that each tray contains the correct mass of ingredients, compensating for minor variations in deposition or biscuit absorption. Once inspection is complete, trays move to sealing stations. Transparent film or lids are applied using mechanical arms with pneumatic actuators. Vacuum or controlled atmosphere sealing may be applied in some systems to extend shelf stability without altering texture. Labeling machines print batch codes, production dates, and other required data on lids or shrink sleeves, using high-resolution thermal printers synchronized with conveyor motion. Finished and packaged tiramisu trays are then conveyed to palletizing robots. Each layer of trays is stacked systematically, maintaining geometric stability. Stretch film is applied in tight spirals around the stack to secure pallets for refrigerated storage. Temperature and humidity sensors within the storage area ensure that the dessert maintains optimal conditions until distribution. Refrigerated transport. Systems continue this temperature-controlled environment, preserving texture, flavor, and visual quality. Throughout production, stainless steel pipelines connect each step. Cheese preparation, egg blending, coffee brewing, biscuit soaking. layering, and packaging. Pumps regulate flow, while automated valves control timing and volume precisely. Temperature probes, viscosity meters, pH sensors, and weight scales provide real-time data to the central control system, allowing fine adjustments in process parameters without manual intervention. Each transformation, from raw cheese and eggs to layered cocoa top dessert, relies on precise mechanical and thermal control. Optional flavor modifications, such as chocolate shavings or alternative liqueur blends, are introduced at designated stages using metered dispensers. High-speed augers fold additives into the mascarpone mixture without breaking the gel, ensuring uniform distribution. When applied to the surface, sprinkling systems position toppings precisely without disturbing the layers below. Quality assurance tests occur at multiple stages. Rheometers evaluate the spreadability and firmness of the mascarpone mixture. Moisture analyzers verify that ladyfingers retain enough liquid to be soft but not soggy. Refractometers measure sugar concentration in both the custard and coffee liqueur blend. Visual inspection ensures color consistency, and spot microbiological sampling confirms the effectiveness of pasteurization and safe storage. The final product exhibits precise physical properties: a dense yet creamy mascarpone layer with stable gel structure, a sponge layer of ladyfingers soaked to optimal moisture content, and a fine cocoa powder surface finish. The internal protein and fat matrix supports the structure while retaining a soft, spoonable texture. Each spoonful reflects careful coordination of ingredient ratios, temperature, shear forces, and layer integration. Even at a microscopic level, the structural integrity is controlled. Proteins in the mascarpone form a cohesive network, trapping air minimally. Fat droplets are distributed evenly, and moisture from coffee infusion is absorbed uniformly in the sponge layer. Cocoa particles adhere lightly to the top without penetration, ensuring visual consistency and flavor profile. Dr. Pepper is manufactured by preparing a concentrated flavor syrup, blending it with treated water at a precise ratio, carbonating the finished beverage to a fixed dissolved CO2 level, then filling and sealing containers under conditions that prevent loss of carbonation and flavor. Production starts with water because it is the largest component and it sets the baseline for taste and carbonation behavior. Incoming water is filtered to remove suspended solids and then polished through fine filtration to tighten clarity. Mineral content is adjusted to a target profile because hardness and alkalinity change how acidity and flavors present. The water is then cooled because colder liquid absorbs CO2 more efficiently and gives more stable carbonation control. While water is being prepared, a sweetener stream is built. Depending on the formula, this can be a sugar syrup or a sweetener solution that behaves like syrup in dosing. Granulated sugar is dissolved in heated tanks with agitation until the solution is clear. The syrup is filtered to remove undissolved crystals that could seed crystallization later. Syrup concentration is monitored by density, so every batch has the same sweetness potential per liter. A separate flavor concentrate is prepared as a high-strength blend that will later be diluted. Flavor components are staged in small tanks and metered by weight into a blending vessel. Many flavor components are carried in alcohol or in emulsified oils, so they stay stable in water. High shear mixing is used to disperse oil-based components into a uniform emulsion that will not separate during storage. The concentrate is filtered to remove any particulate and to protect dosing valves. Acid addition is managed early in the syrup phase because acidity affects microbial stability and also changes flavor perception. Acid is prepared as a liquid solution for accurate metering. It is injected into the syrup or into the flavor concentrate depending on the line design. pH is measured and adjusted to a tight set point because small shifts change the balance between sweet and sharp notes. Buffer salts can be used in very small amounts to stabilize pH drift. If the product uses caramel color, it is handled as its own dosing stream. Caramel color is stored in tanks with gentle mixing because it can stratify. It is metered into the syrup blend at a controlled rate. Inline color measurement can be used to confirm shade stability across the run. Color is stabilized by keeping oxygen pickup low and by avoiding excessive heat exposure. Once sweetener, flavor, acid, and color are prepared, they are combined into a finished syrup. This syrup is the concentrated recipe that will be proportioned into final beverage. The syrup is mixed in a tank with controlled agitation that avoids foaming. Foaming traps air and later interferes with carbonation. The finished syrup is held at a controlled temperature and then delivered to the blending system through metered pumps. Final beverage blending is commonly done with a proportioning blender. The blender meters syrup and treated water by mass flow or by volumetric flow with density compensation. The ratio is the key control point because it determines sweetness and flavor intensity. Ratio control is verified by measuring soluble solids in the blended stream and comparing it to a target. When the ratio drifts, the control valves adjust in real time. Before carbonation, the blended beverage is typically deaerated. Deaeration removes dissolved oxygen and trapped air. Oxygen dulls flavor over time and also reduces carbonation efficiency. Deaeration is done under vacuum, where the liquid spreads as a thin film. Vacuum pulls gas out and the liquid leaves with lower oxygen content. The beverage is kept cold during this step to preserve volatile flavor notes. Carbonation follows deaeration, and it is controlled by temperature, pressure, and contact efficiency. CO2 supply is filtered and regulated to a stable pressure. The beverage enters a carbonator, where CO2 is injected and dissolved under pressure. The carbonator can use a packed column or a sintered stone system that creates fine bubbles. Fine bubbles create high surface area and improve dissolution. Pressure is held high enough to drive CO2 into solution and to prevent breakout. Dissolved CO2 level is monitored continuously. The measurement can be inferred from temperature and pressure or measured directly with inline instruments. The line targets a defined carbonation volume that matches the intended bite. If temperature rises, CO2 solubility drops, and the instrument will show a fall in dissolved gas. The system compensates by raising pressure or by improving cooling. Stable cooling is therefore central to carbonation consistency. Once carbonated, the beverage must be handled gently. High shear pumps can cause CO2 to break out and create foam. The line therefore uses low shear pumps and smooth piping with gradual bends. The product is kept under pressure all the way to the filler. Pressure maintenance prevents carbonation loss and also prevents foaming at the fill valve. Container preparation runs in parallel with beverage preparation. For cans, the empty cans are conveyed and cleaned with air and rinsing systems. For bottles, the containers are oriented and presented to the filler. Plastic bottles may be produced nearby by blow molding and then transferred quickly. Glass bottles arrive as formed containers and are staged for feeding. All containers are timed, so the filler receives a continuous flow without gaps. Filling is done on counter-pressure equipment for carbonated beverages. In a counter-pressure filler, the container is first pressurized with CO2 to match the bowl pressure. This reduces foaming during liquid entry. A fill valve then opens and beverage flows in with controlled velocity. Fill height is controlled by a level probe or by timed volumetric control. Once filled, the valve closes and pressure is released in a controlled way so the liquid does not erupt. Foam control at the filler is managed by temperature and valve design. Cold liquid reduces foam because gas stays dissolved. Smooth valve surfaces reduce nucleation points where bubbles form. Fill tubes can deliver liquid down the side of the container to reduce turbulence. Turbulence increases foam and can cause underfills. The filler, therefore, balances speed with smooth flow. After filling, the container is sealed immediately. Cans are sealed by seaming, where a lid is placed and rolled into a tight seam. Seam geometry is controlled by roller, profiles, and force. Seam integrity is critical because a tiny leak will release CO2 and flatten the product. Bottles are capped with controlled torque. Torque control ensures the seal is tight without damaging threads. Headspace management is part of carbonation retention. A defined headspace volume is left above the liquid. This headspace contains CO2, which will equilibrate with the dissolved CO2. If headspace is too large, carbonation can be lower at equilibrium. If headspace is too small, fill accuracy becomes difficult and overflow increases. Many lines use a CO2 jet just before capping to displace air in the headspace. This reduces oxygen and improves flavor stability. Once sealed containers move to coding and inspection. Date codes are printed by inkjet or laser systems. Inspection checks can verify fill level and cap presence and seam quality. Seam inspection on cans can include thickness checks and overlap checks. Leaker detectors can find micro leaks by pressure decay or vacuum methods. Out-of-tolerance units are rejected automatically. If the line produces multi-pack products, the sealed units are collated next. Cans can be wrapped in film or placed in cartons. Bottles can be grouped into shrink packs or tray packs. Shrink film is applied and then heated to conform around the pack. Heat is controlled so the film shrinks without overheating the product. Cartons are erected and loaded with gating systems that maintain alignment. Case packing follows. Packs are arranged into cases with patterns that protect seams and caps. Cases are sealed and labeled. Palletizing stacks cases to minimize movement and to keep load stable. The product is then stored and distributed with temperature control practices that reduce carbonation drift. Sprite is manufactured by preparing a citrus flavor syrup, blending it with treated water at a fixed ratio, carbonating the beverage to a precise dissolved CO2 level, then filling and sealing containers under counter. Pressure, so carbonation and aroma stay stable. Production starts with water because water chemistry controls acidity perception and carbonation behavior. Incoming water is filtered to remove suspended solids and then polished through fine filtration. Mineral content is adjusted to a target hardness and alkalinity so the final drink has consistent bite. Water is then cooled because colder water holds CO2 more efficiently and reduces foaming during filling. A sweetener stream is prepared in parallel. For sugar-based production, granulated sugar is dissolved in heated tanks with agitation until the syrup is clear. Syrup concentration is measured by density and held in a narrow band because it determines final sweetness after dilution. The syrup is filtered to remove undissolved crystals that could seed crystallization or clog valves. For other sweetener systems, a concentrated solution is prepared and handled as a metered liquid feed with consistent density. The citrus flavor system is built as a concentrate that can be dosed precisely. Lemon and lime flavor components often include oil-based fractions that must be emulsified to remain stable in water. The flavor concentrate is mixed in a blending tank where carriers and emulsifiers are combined with flavor oils. High shear mixing reduces oil droplet size and stabilizes the emulsion. Droplet size control prevents separation and reduces ring formation at the surface of the final beverage. The concentrate is filtered to remove any particulate and to protect dosing pumps. Acid addition is managed as part of syrup formulation because pH defines freshness and also affects how sweetener is perceived. Acid is prepared as a liquid solution for accurate dosing. It is injected into the syrup or into the flavor concentrate depending on process layout. pH is measured and adjusted to a tight set point. Small changes in pH shift the balance between sharp citrus and sweetness. Buffer salts can be used in very small amounts to reduce drift, but the main control is acid dose. If the formulation includes a clouding system to support the citrus profile, it is prepared as an emulsion stream. Cloud systems are designed to keep a slight visual opalescence and to carry flavor. They are mixed under shear and then held with gentle agitation so they do not cream. Stability is verified by checking droplet size and separation rate. Once sweetener syrup, flavor concentrate, acid, and any cloud system are ready, they are combined into a finished syrup. The syrup is mixed with controlled agitation that avoids foaming. The syrup is then held at a stable temperature and delivered to the proportioning blender through metered pumps. Filters at this stage protect the blender and carbonator from particles and gel lumps. Final beverage blending is done with a proportioning system that meters syrup and chilled treated water. The ratio is controlled by mass flow meters or by volumetric meters with density compensation. Ratio accuracy is the main determinant of consistent taste. The blended stream is monitored by inline soluble solids measurement. When solids drift, the control system adjusts valve positions to correct the syrup-water ratio. Before carbonation, the blended beverage is commonly deaerated. Deaeration removes dissolved oxygen and entrained air. Oxygen dulls citrus aroma over time and increases oxidation in flavor components. Air also reduces carbonation efficiency because it occupies headspace in the carbonator and promotes foam. Deaeration is performed under vacuum where the beverage spreads as a thin film. Vacuum pulls gases out and the liquid leaves with lower oxygen content. Carbonation follows, and it is controlled by temperature, pressure, and contact efficiency. CO2 supply is filtered and regulated to stable pressure. The cold beverage enters a carbonator, where CO2 is injected and dissolved under pressure. Many carbonators use a sintered stone or injector that forms fine bubbles. Fine bubbles create high surface area and dissolve quickly. The carbonator maintains a pressure high enough to keep CO2 in solution and prevent breakout. Dissolved CO2 level is monitored continuously. Instruments measure or infer carbonation based on temperature and pressure. The line targets a defined carbonation level that gives a crisp bite. If temperature rises, CO2 solubility drops and gas begins to break out. The system compensates by increasing pressure or improving cooling. Tight temperature control in the blending and carbonator sections therefore supports stable carbonation. Once carbonated, the beverage must be handled with low turbulence. High shear pumps and sharp piping bends can release CO2 and create foam. The line uses low shear pumps and smooth piping layouts. The product is kept under pressure all the way to the filler bowl. Pressure maintenance prevents CO2 loss and reduces foaming at the fill valve. Container handling runs in parallel with beverage. Preparation. Cans or bottles are conveyed, oriented, and cleaned. Cans are often rinsed and drained before filling. Bottles are oriented and may be rinsed or air-blown to remove dust. Plastic bottles may be supplied from blow molding and then transferred to the filler quickly. Container temperature can influence fill behavior because warm containers promote foaming. Lines manage container staging to avoid excessive warming. Filling is performed on counter-pressure fillers. The container is first sealed to the fill valve and pressurized with CO2 to match filler bowl pressure. This equalization reduces foaming when liquid enters. The fill valve opens and beverage flows in at a controlled rate. Fill level is controlled by a probe or by timed flow depending on equipment design. Controlled flow reduces turbulence and helps maintain carbonation. After the container reaches fill level, the valve closes and pressure is released in a controlled way. Controlled release prevents the liquid from erupting and prevents excessive foam that could contaminate the seal. For cans, the lid is applied and the can is seamed immediately. For bottles, the cap is applied immediately with controlled torque. Rapid sealing locks carbonation and reduces oxygen pickup. Headspace control is part of maintaining carbonation and flavor. The fill is set to leave a defined headspace volume. Many lines apply a CO2 jet just before capping or seaming. This displaces air from the headspace and reduces oxygen content. Reduced oxygen protects citrus aroma and reduces flavor drift. Headspace CO2 also supports equilibrium carbonation by providing a gas reservoir above the liquid. After sealing containers, move to inspection. Fill level inspection checks for underfills and overfills. Cap inspection checks for missing caps and skewed caps. Seam inspection checks seam thickness and overlap on cans. Leak detection can identify micro leaks that would cause carbonation loss. Out of specification units are rejected automatically. If the product is packed into multi-packs, the sealed units are collated next. Cans can be wrapped in film or placed in cartons. Bottles can be grouped in shrink packs or tray packs. Shrink film is applied and then heated to conform around the pack. Heating is controlled so it shrinks film without overheating the beverage. Cartoning systems erect cartons and load units with gating systems that maintain spacing. Canada Dry ginger ale is manufactured by preparing a ginger citrus flavor syrup, blending it with treated chilled water at a fixed ratio, carbonating the beverage to a controlled dissolved CO2 level, then filling and sealing containers under counter pressure so carbonation and aroma remain stable. Production starts with water because it defines the baseline taste and the way carbonation behaves. Incoming water is filtered to remove suspended solids and then polished through fine filtration. Mineral content is adjusted to a target profile because hardness and alkalinity change perceived sharpness and sweetness. Water is then cooled because colder liquid absorbs CO2 more efficiently and reduces foaming at the filler. A sweetener stream is prepared in parallel. For sugar-based production, granulated sugar is dissolved in heated tanks with agitation until the syrup becomes clear. Syrup concentration is monitored by density because it determines final sweetness after dilution. The syrup is filtered to remove undissolved crystals that could clog valves and create settling. For alternative sweetener systems, a concentrated sweetener solution is prepared and handled as a metered liquid feed with stable density. The ginger flavor system is built as a concentrate that can be dosed precisely. Ginger character often includes both water-soluble notes and oil-based notes that need controlled dispersion. Flavor components are staged in small tanks and metered by weight into a blending vessel. Oil-based fractions are emulsified so they remain stable in the final beverage and do not separate in storage. High shear mixing reduces oil droplet size and improves emulsion stability. The concentrate is filtered to remove any particulate that could seed haze or block nozzles. Acid addition is managed as part of syrup formulation because pH controls brightness and stability. Acid is prepared as a liquid solution for accurate metering. It is injected into the syrup blend or into the flavor concentrate depending on line design. pH is measured and trimmed to a tight set point because small shifts change the ginger bite and the perceived sweetness. Buffer salts can be used in very small amounts to reduce drift, but the main lever is acid dose. If the formula uses a color system or a cloud system, those are handled as separate dosing streams. Color is held in tanks with gentle mixing and metered into the syrup at a controlled rate. Cloud systems are prepared as emulsions that remain suspended and carry aroma. Cloud emulsion. Stability is controlled by droplet size and by the choice of emulsifier. These streams are filtered and then injected into the syrup blend under controlled mixing. Once sweetener syrup and flavor concentrate and acid and any supporting streams are ready, They are combined into a finished syrup. Mixing is designed to create uniformity without entraining air. Air entrainment creates foam and reduces carbonation efficiency later. The finished syrup is held at a stable temperature to keep viscosity consistent for metering. It is delivered to the proportioning blender through metered pumps and protected by final inline filters. Final beverage blending is done with a proportioning system that meters syrup and chilled treated water. Control can be mass flow based or volumetric with density compensation. Ratio accuracy is the main determinant of consistent taste from run to run. The blended stream is monitored by inline soluble solids measurement as a proxy for syrup ratio. When solids drift, the control system adjusts valves to correct the ratio in real time. Before carbonation, the blended beverage is typically deaerated. Deaeration removes dissolved oxygen and entrained air. Oxygen can dull delicate ginger notes over time and can change aroma character during storage. Air also interferes with carbonation by promoting foam and reducing CO2 dissolution efficiency. Deaeration is performed under vacuum, where the liquid spreads as a thin film. Vacuum pulls gases out and the liquid exits with lower oxygen content. Carbonation follows deaeration and is controlled by temperature and pressure and contact efficiency. CO2 supply is filtered and regulated to stable pressure. The cold beverage enters a carbonator where CO2 is injected under pressure. Injection often uses a sintered stone or fine bubble injector to create small bubbles with high surface area. High surface area improves dissolution speed and reduces large bubble breakout. The carbonator maintains pressure high, enough to keep CO2 in solution. Dissolved CO2 is monitored continuously by instrumentation or by calculation from pressure and temperature. Temperature is a critical variable because CO2 solubility drops as temperature rises. The system compensates for temperature drift by adjusting pressure and by tightening cooling upstream. Stable chilling of water and blended beverage is therefore essential for consistent carbonation. Once carbonated, the beverage must be transported with minimal turbulence. Turbulence releases CO2 and creates foam, which leads to fill problems and carbonation loss. The line uses low shear pumps and smooth piping layouts. Sharp bends and sudden diameter changes are avoided. The product remains under pressure from carbonator through filler bowl to keep gas dissolved. Container handling runs in parallel with beverage preparation. Cans or bottles are conveyed and oriented and cleaned. Cans are typically rinsed and drained before entering the filler. Bottles are oriented and can be air rinsed or lightly rinsed, depending on line design. Plastic bottles may be supplied from blow molding and transferred quickly to avoid dust pickup. Container temperature matters because warm containers promote foaming. Staging is designed so containers do not heat excessively before filling. Filling uses counter-pressure equipment designed for carbonated beverages. Each container seals to a fill valve and is pressurized with CO2 to match the filler bowl pressure. Pressure equalization reduces turbulence when liquid enters. The fill valve opens and beverage flows in at a controlled rate. Fill level is controlled by a level probe or by timed flow depending on the filler type. Smooth flow is critical because foaming can cause underfills and messy seals. After the target fill level is reached, the valve closes and pressure is released in a controlled way. Controlled release prevents eruption and reduces foam at the top. Cans are then lidded and seamed immediately. Seam rollers form a tight double seam that locks the lid to the can body. Seam geometry is controlled by roller profiles and force because seam, overlap, and tightness determine leak resistance. Bottles are capped immediately with controlled torque. Torque control ensures sealing without damaging threads or liners. Headspace control supports carbonation retention and aroma stability. A defined headspace volume is left above the liquid. Many lines apply a CO2 jet just before sealing. This displaces air in the headspace and reduces oxygen pickup. Reduced oxygen helps keep the ginger aroma crisp during storage. Headspace CO2 also supports equilibrium between dissolved CO2 and gas phase CO2. Immediately after sealing containers, move through inspection. Fill level inspection checks for underfill and overfill. Closure inspection checks for missing caps or misapplied lids. Seam inspection on cans can include overlap checks and thickness checks. Leak detection can identify microleaks by pressure decay or vacuum methods. Out of tolerance units are rejected automatically to protect product consistency. If the product is produced in multiple packaging formats, the downstream handling changes slightly, but the goals remain the same. For multi-packs, cans are collated and wrapped in film or loaded into cartons. Bottles can be arranged into shrink packs or tray packs. Shrink film is applied and then heated to conform around the pack. Heat application is controlled so the film shrinks without overheating the beverage and driving CO2 loss. Cartons are erected and loaded with gating systems that maintain spacing and prevent scuffing.